Okay, good morning to everybody. My name is Ashish Dutta, and I'm the program chair of the Advances in Robotics Conference, AIR 2021. So welcome to IIT Kanpur, although virtually. We wish that we could have met, you could have come here and we could have met, but unfortunately that did not happen, but still we are meeting virtually online. So today is the first day of the conference, and we start off with a workshop, which is the Robotics Society of Japan and the Robotics Society India workshop on robotics in Japan and India. So we have 4 speakers from either side, and we also have the presidents of the Robotics Society of Japan and the Robotics Society of India. So first of all, we'd like to invite the speakers and the respective presidents to come on stage. So you'll be brought on stage one by one. So we would like to invite
Hello, can you hear me?
Yeah, yes.
Yeah.
We will bring you on stage. So please wait one by one. Everybody will be coming on stage.
Okay. Thank you.
Yeah, good morning. We still have Professor, who is left? Professor Santanu Chaudhury.
Santanu has not joined. And Ekta is there.
Yeah, and Dr.
Professor
Murakami.
Chaudhury will have to turn on mic and camera. Yeah, he's doing.
Okay, and President of RSJ.
Yes, Professor Asada.
No. I'm a former president, Murakami.
Okay.
Sorry, it is Murakami.
Dr. Murakami.
Yeah,
Yes.
Hiroki
Yes.
Murakami.
Okay. So, Professor Murakami.
Yes.
Yes.
Oh yeah.
Yes.
Oh, super.
So everybody is on stage. Let me just check once.
Ekta,
Yeah.
She said she will join.
Okay. Yeah, I think everybody is on stage.
I don't see Ekta.
No, Ekta is there. I think her mic is turned off.
Yes, I'm here.
Oh, good morning, Tom.
Thank you very much for your all efforts. And it's great that everybody is using their virtual background.
Okay. Yes,
Actually,
yes.
I can't. That's why I'm now using the application for my background.
Okay.
Anyway, it's, yeah.
Okay, so I think everybody is on stage, although some of us might not have turned on the camera, so they're not visible, but I think everybody is on stage. Okay, so I think good morning and welcome to this international conference, Advances in Robotics, AIR 2021. Today is the first day and we are starting off with the workshop. So I'm very grateful to our speakers from Japan who have spared their time to come here. So to our speakers from Japan, Ohayo gozaimasu and yoroshiku onegai shimasu. This is our first workshop. Let's hope that we'll have many more workshops like this in the future. Now, I'd like to request Director of the Robotics Society India, Professor Santanu Chaudhury, to speak to our gathered audience and to welcome the participants.
Good morning. Thank you, Ashish. Dear Professor Murakami, President of Robotics Society of Japan, office bearers of the Robotics Society, and the audience who have joined for this workshop here, and on the first day of the conference of AIR 2021, warm greetings to all of you. This is a unique start for this conference through a workshop, an Indo-Japan workshop on robotics. In fact, our old friend Shibata is here, and if we go back in time, I think that society, the robotic society in India, was also motivated by Shibata's inspiring words. So we are really thankful to Shibata to start this whole activity, and as a follow-up of this friendship, we are having this first workshop, and we hope to have that workshop many more times in future. In fact, today, if we look at with advances which are happening in machine learning, artificial intelligence, the robotics is moving to a different plane altogether. The science of engineering, science and engineering of intelligence is bringing in a new dimension to the robotics. And the gaps we need to address in order to advance how the machines will help people reliably with cognitive and physical tasks is a key question. So the advances of robotics is moving closer to being more human. And in this context, the dependability that what we are talking about in the AI field is also equally valid and significant in robotics as well. Robo is expected to work in a variety of tasks in conjunction and collaboration with human beings. So dependability is a critical criteria of design of a robotic system. And we have seen the collaborative robotics coming up in a big way globally, which in an Indian context has a utility in terms of enabling increased productivity by the human workers and not robots replacing human workers, because this is a question which is always raised in the Indian context, and the use of robotics for efficiency is definitely a requirement for industrial growth. Very interestingly, I was just looking at some of these literatures. We found that International Federation of Robotics, their award in 2021 for innovation and entrepreneurship in robotics went to a product called Pixel Paint, which is a technology of ABB, where the two robots in synchronization can paint cars and with the different patterns. And it also claims, and which is valid, that is a green footprint because the wastage of paint is minimal by use of those synchronized robotic arms. And in fact, therefore, we are moving to another context and aspect of robo, that to ensure sustainability, to reduce carbon footprints, robots also can play a very critical role. And today's pandemic has also indicated, particularly in the Indian context, what is called market pool-based robotics technology development. In fact, last 1 year, we have seen a number of new companies coming up with service robots which can help and work in the hospitals, particularly to add on to the health workers because of this COVID, the infectiousness and how that can be handled through robotics. And there has been a huge initiative and enthusiasm in Indian innovators working in this space, and which is absolutely an user-directed and need-directed. So in an Indian context, a need-directed service robotics is really coming into its own, and I think that space will also grow, because this is something which is important and interesting for us to look at and work together with Japanese scientists to have a substantive innovation in these spaces. We have also looked at in India, the use of drones have increased substantially. And new DST, science and technology policy, has opened up huge avenues for exploiting geospatial data and activities in the geospatial space. And in this context, drones and intelligent drones and aerial robotic manipulators today comes with huge business potential in Indian context, particularly in terms of actions and activities in remote areas. I think this is another, I'm just touching upon some of these things. This is because this is something which is, there has been a significant development in Japan, and where we can actually collaborate and work together. And 5G, if you see the 5G coming in, and which we expect will happen in India towards the end of this year, with two major telecom operators, Airtel and Jio, coming in a big way, will also change the way the robotics we practice globally as well as in India. In fact, cloud robotics is today becoming a reality, and this will actually enable us to have robots built with much less energy footprint and compute footprint, and use them for a variety of applications. And keeping these things in mind, I think we need to look at a new generation of robotics research, which gets more directly and intimately connected with demands, both industrial and human demands. But here possibly, another point we cannot ignore, which in the context of the debate which is happening in India with reference to AI. In fact, the think tank, Niti Aayog, has initiated discussions on ethics of AI. And globally also, we are talking about robo-ethics. And this in our country right now is not of much focus. Although ethics in AI is coming in, but along with it, it's also necessary to look at robo-ethics if the robo gets used more in industrial context, in defense context, in service context, in healthcare and other places. So I feel that this is a very exciting time for robotics, and where we really have convergence of multiple technologies. And at that point, this joint workshop, I look forward to initiation of joint activities and long-term activities between Indian scientists and scientists from Japan, under the aegis of the Robotic Society and the Robotic Society of Japan. I think this should be a new future of robotics in India as well as in global context. Thank you.
Thank you. Thank you, Professor Santanu Chaudhury, for your inspiring words and the way ahead and the way forward. Next, I would like to request Murakami Sensei to please deliver his address from RSJ, the Robotic Society of Japan.
Okay, thank you. So I introduced our activity. So I get display. Can you see the slide?
Yes. Yes.
Okay, so I'm Hiroki Murakami, the 20th president of RSJ Robotic Society of Japan. And first, I'm glad to be held the first workshop, RSJ and TRS workshop, robotics in Japan and India, and congratulations the 10 years anniversary the Robotics Society India TRS.
村
So,
上会長は、プレゼンテーションモードにしてください。
プレゼンテーションモード。OK。
はい。
これどうする？
今、編集モードになってます。
編集も、これだ。わかった。Is it OK? 大丈夫ですか？
Not yet.
Not yet.
Not yet. 違う画面になってるみたいですね。違うスク
違う
リーンを。
OK。ちょっと待ってね。わかった。どうすればいいんだ？ちょっと待ってよ。
一回共有を外していただいて、
はい。
OK。
一回共有を外して、それで、パワーポをプレゼンテーションモードにして、その画面を選べばいいと思います。
そういうことですね。ちょっと待ってください。
はい。Sorry for Japanese communication. 一回共有を外してもらって、
ちょっと待って、どこに行けばいいんだ？これを外す。
はい。で、パワーポをプレゼンモードにして、はい。
あれで、どうすんの？ウィンドウ1個しかないとき。
1個しかないですか？じゃあ、そのウィンドウが、パワーポに表示になってます。プレゼンテーションモードに。
今はなってるけど、スライドショー、プレゼンテーションモードってどれ？
じゃあ、スライドショーでいいです。スライドショーでいいです。
スライドショーにしちゃうと、今、ウィンドウ1個しか持ってないので、スライドショーにすると元のとこへ、わかった。どうやって行くのこれ。
行きませんか。
Murakami sensei, you can please stop sharing.
Yes. Yes.
Then you share. Okay. Then share and then choose window.
Choose window. Yes.
Okay. Then you can, in your window, you can go to the PowerPoint.
PowerPoint, yes. これだよね。で、これで、and share.
Share.
これで、
同じ。
同じ。
いいじゃないか、これで。
Sorry.
No problem. I think we can continue.
I think this is fine, right?
It's fine. We can read.
Yeah, fine.
はい。じゃあ、メニューをダブルクリックして、そうですね。大きくしていただいて、そうです。
Yes.
で、これをこうする。
そう。OK です。OK。
Sorry. So, according to the history I hearing, in 2010, Professor Shibata started working on the establishment of the Robotics Society in India under the direction of Professor Tomasa Sato, the 13th president of RSJ, and Professor Sadao Kamura, 15th president of RSJ. So, Professor Shibata discussed Professor Saha and the Professor Dutta, and they realized the establishment of the Robotics Society, TRS, India in only 1 year. I respect to the effort of Professor Shibata and tremendous activity of Professor Saha and Professor Dutta. And in this March, TRS and RSJ President meeting was held. President Asokan and former President Asada agreed to be held this workshop. So I hope that the cooperative relationship between RSJ and TRS will continue in the future. So let me take a moment to briefly introduce the Robotics Society of Japan. Usual. Okay, so the Robotics Society of Japan was established in 1983. The practical application of the industrial robot began to progress in automotive industry and other industries in about 1983. So main robotics topics of those days was mechanism and control engine or other kind of the engineering. But about 40 years have passed since then. So robots has been used on not only in industry fields but also in various environments. For these reasons, the Robotics Society of Japan is promoting domestic and international activities that these on. And okay, so especially the international journal is Advanced Robotics and globalization activities in these. よいしょ。これだな。In many academic society in Japan, the number of the members is decreasing, but the Robotics Society of Japan is keeping about 400 members. The number of the supporting members decreases with recession of Japan around 2000, but recently it has increasing slightly due to the policy of robot revolution in Japan. This これ動かない。よいしょ。あ、そっか、こうだ。And this is the domestic journal. Almost all articles are written in Japanese, and all papers are open access online. And Advanced Robotics, the International Journal of the Robotics Society of Japan, has been published since 1988. And this is publishing by Taylor and Francis. あ、そうか。よいしょ。This journal is subscribed by many libraries, so please use it for research on previous research. And the submission fee is free, and AR get the impact factor, so please submit your research result. よいしょ。RSJ annual conference and collaborative symposium is held in Japan every year. But unfortunately, 2020 and 2021 become online conference due to the influence of the COVID-19. よいしょ。And Robotics Society of Japan co-sponsored two conferences. Maybe you know. So one is IROS, IEEE RSJ International Conference on Intelligent Robotics and Systems from 1988. And IROS 2022 will be held on Kyoto, Japan. So please participate in IROS 2022 on site, I hope. And another one is Roman International Symposium on Robot and Human Communication. And so maybe you know, Roman was an excellent success in 2019 in India. And fortunately, I have a chance to visit India first time, that conference. よいしょ。あれ？あ、そう。And RSJ give these hours every year, and especially the best paper award in AR received prize money from T&F as a supplement prize. So please activity submit AR. And this is あ、違うな。よいしょ。This is the official website of the RSJ. Basically, Japanese site, but we are also actively working on to enhance the English page, this one. So please contact our website. And another one is the Robogac page is a page of the information that can be understood not only by engineer and researcher, but also by the general people. So recently, mainly a Japanese page, but recently machine translation technology has advanced, so please read these pages. Another activities contribute to education. We have we do the International Robotics Forum for high school students from 2013. So it will be held with IREX International Robot Exhibition. So thank you for your attention. I hope the collaborating relationship between RSJ and TRS will contribute to the future. I look forward to seeing you on site after the COVID-19 will be over. Thank you.
Thank you. Thank you, Murakami Sensei, for your kind words and telling us the history of the Robotics Society of Japan and its various activities, and also wishing that we have further collaboration between the Robotics Society of Japan and the Robotics Society India. Now, I would like to request Professor Asada, as the former president of RSJ, would you like to say a few words as you are here?
Almost nothing. I suppose maybe time is already behind the schedule. So I suppose maybe we should start immediately the workshop.
Okay.
Thank you for the everything, because actually Tom Shibata sensei initiated this workshop, and I'm happy when I was the president, and now I'm the former president, and I give my talk tomorrow. Okay, anyhow, so let's start the workshop. Thank you.
Okay, thank you, Asada Sensei. Okay, so I think we can move on to the next part, that is the presentations. So the program today is we have 4 speakers from Japan, and we have 4 speakers from India. So first we'll have 4 speakers from Japan. First is Professor Tomohiro Shibata from QTech, to be followed by Professor Kanako Harada, University of Tokyo, then Professor Kimotoshi Yamazaki from Shinsu University, and then Professor Jonte Venture from Tokyo University of Agriculture and Technology and AIST. So each speaker would please present for about 20 minutes, and we can have the question answer at the end of the session. Okay, so I request Professor Tomohiro Shibata to please start the presentation from the Japan side.
Yes, thank you very much, Professor Dutta. I'm really honored, and congratulations again on your 10th anniversary. And thank you very much. So I'm really honored by that director, Santanu Chaudhury, and also Professor Dr. President, our president, and also Asada Sensei, and Murakami and Asada Sensei, mentioned my name regarding to this workshop and the relationship between us. Thank you very much. And due to the time limitation, I really quickly, pass through the slides as fast as possible. Okay, so today I have there is a time limitation, so I can't explain all the robotics research at QTech, but try to do it a little bit. And so actually, it was 2007 that I first visited IIT Kanpo. And after that, fortunately, I and the professor, at that time, Associate Professor Dutta, got a grant, fortunately, a JST, DST, and Strategic Cooperative Program. And we have exchanged it. We exchanged it, right? So I visited also my professor and also my students visited Kanpo, and also vice versa. And if you watch this, I'm sorry if you watch this. This is Todai Temple, the biggest temple, wooden temple, right? So in Japan, and here is Professor Behera and Professor Ashish Datta, and also Anupam Saxena. So they visited us, right? And I also visited, of course, I and Associate Professor Tamei visited, and this is a season that we have to be colored like this. So we celebrated the Holi like this. Right, and this some typical good movie for our collaboration, so actually we are good at working with EMZ signals interpretation, and Professor Datta's team was good at producing this 3D printed finger exoskeleton for rehabilitation. So we collaborated together in a very good manner, and we also printed this exoskeleton at NICE. At that time, I was associate professor of NICE. Yeah, and in that way, we did a very good collaboration. So I was really lucky. Thank you very much, Ashish, again. And okay, so that's a brief introduction of my relationship with India. There are so many slides more, but no time today. And here, so I am a professor of QTech and in Kitakyushu City of Japan, and it is here. And this is Kyoto, and this is Tokyo, and this is Osaka. But by flight, it's 1 hour flight from Tokyo, 1.5 hours flight in Tokyo. And I hope many of you know Yasukawa Electric Corp, since it also has a division in India, and they hold the best industrial robot cell. Their share is one of the best in the world, and you also know Kanako, Yasukawa Electric Corp has been doing really good. And why I'm telling this is because QTech was founded by this Yasukada family. So in 100 years, 110 years ago. So that's why I'm telling this. And the Yasukawa's headquarters is in Kitakyushu City. And of course, and we also collaborate very well. And actually, recently, they're also interested in food technology. So in this respect, we are also working together. Okay, next, I would like to introduce the homepage of our Center for Software Synthesis. And as Director Chaudhury mentioned, yes, sustainability is a very important issue, even in our country, of course. So that's why towards sustainability, we have been doing a lot of things with many professors and associate professors and also assistant professors, many staffs. Okay, so to create new robot market by realization and demonstration, this is our one of the most important features towards sustainability establishment. And there are many fields that we are working: feed robot consortium, agri-robot consortium, agri-robot, and medical and care support, and industrial robot. So unfortunately, I don't have time to explain them in detail. Just I'd like to know, they are doing a lot of, so actually our center has been working with holding many different types of competitions. And this is actually a world competitions that's also organized very well by, supported by, strongly initiated and supported by Professor Ayusawa. That's Robocup. And we are good at also football playing, robot. But also here, I just would like to introduce our service robot briefly. So Hideki no Musashi at Home is a student circle, and they're really strong. They have been really strong. So this is a robot given by Toyota, and so we are working. So the student team has been working with intelligence, and actually they won 3 times. 2 in this Robocup at Home, and 1 is World Robot Summit conducted by a Japanese ministry, right? Like this. Yes. Okay. And let me move on to this slide. And so due to the significant problem of super aging in Japan, so we are having shortage the caregivers and also all the workers in any areas. And this slides focus on the healthcare. And the different robots and technologies are needed for different health conditions. And you see wearable sensors, walking assist devices, and some motor learning assist, dressing assist, advanced home life support. So there are most of them actually. Shibata Laboratory has been working on most of these robots and intelligent robotics. And only for this picture. So this is for toilet assistance robot. And it can be also used for stand assist. And this is driven by Associate Professor Wagatsuma of our department too. Okay, and my recent talks actually available on the net. So please, visit these sites. One is first webinar, one talk was given for first webinar by TRS, and my title was Robots for Assisted Living. And another one is I gave it an opening talk for ICRA 2021 workshop entitled Learning for Caregiving Robots. Now, please visit. Okay, so just I want to finish my part by introducing the young researchers, right? Young promising researchers. So one researcher is Professor Shuhei Itomoto, and actually he was a student of Professor Asada in the past, and also Professor Hosoda, and joined QTech 2 years back. And he's interested in biological, inspired systems and robotics. And I have to, So you can see these robots, so pneumatic actuated robots. And he's interested in these bio-inspired systems, and he's developing robots and algorithms that work for realistic, complicated tasks. And actually, these movies were a relatively old one, and he's already developed a very new, interesting, exciting robot already, but seemingly it's no secret. So he didn't give me a new one. So please visit his website. Okay, the final one. So I also would like to introduce Associate Professor Osa's work. So he's interested in multimodal trajectory optimization for motion planning. So, so as you know, for robotics, there often exist multiple solutions in motion planning, and he can propose a new algorithm that finds multiple solutions simultaneously. For example, in this case, right, the starting point of the hand is the same, but the trajectory are generated are different to the obstacles. The lower movies also show the similar thing. Okay, the hand trajectories are different to avoid avoiding the plant. Okay, so like this, I would like to so close my part, and please visit so please know. So we have a center of for social robotics synthesis, and there are many robotics researchers, and in the many different types of field. Okay, thank you very much, and please visit so these my talks on the internet also. Thank you very much.
Thank you, Tom, for your nice presentation about the research activities at QTech, and also showing us the old pictures regarding your visit to India. So from the participants, if you have any questions, please write down in the Q&A. On the right side, there is a Q&A. So you can write the name of the speaker whom you want to ask the question, and then you can ask the question. Okay, so we would like to save time, so we are not going into the question answer session now. If you have any question, in the Q&A session on the right side of your screen, Q&A, you can write the name of the speaker whom you want to ask the question, write the question, and at the end, we will look at the question answers. Okay, just for saving time. So thank you, Tom, again, for your nice presentation. Thank you. So our next speaker is Professor Kanako Harada from the University of Tokyo. So I would request Professor Harada to please make her presentation. Yeah, Professor Harada, you have to unmute and then turn on the camera.
We lost her.
We have lost her, Rajiv.
Yes, I don't see her in the list now. Yeah, she has again joined.
Okay.
No. Can you hear me?
Yes.
Okay. Can you see my screen?
Yes.
The presentation screen? Yes. Sorry that it seems that my internet is not so good. Can you see my presentation?
It's not the presentation, it's the PowerPoint classical view.
Sorry. Let me. I'm sorry.
Yeah, but the same case with our president. So I think if you're okay, so we are okay.
Yes.
Yes.
Yeah. Okay.
So
then
turn the menu.
So when you share the screen, you have to select the window.
I hope you can. Yes. Now you can see.
It's the same.
Okay.
The same.
It's the same. It's the same.
But the left slice got small already, so that's great.
Okay.
Okay. So I cannot change it to the presentation mode, but I hope that you can I hope this is okay for you.
No problem.
Okay, thank you very much. Sorry that I know that schedule is already behind, but I hope to be quick. And first of all, thank you very much for the wonderful opportunity. I'm Kanako Harada of the University of Tokyo, and I'm talking about the toward automation of surgical robots. And first of all, I'd like to remind you that what are the medical robots? Medical robots are robots designed as medical devices, so they are regulated by the law. And such medical robots include surgical robots and rehabilitation robots. And today I'm talking about surgical robots. Let me talk about a little bit about the evolution of surgical robots. And open surgery is performed even now. And in open surgery, incision is large and the recovery is slow. So it's not good for patient, but surgeon can touch the organ. So it's easy for surgeon. And from 1987, minimally invasive surgery has been developed. In minimally invasive surgery, surgeon insert small tools from small incision. So the recovery can be very fast. But obviously, manipulation is very difficult for the surgeon. Then from 1989, that robotic minimally invasive surgery has been introduced, where the incisions are small and the recovery is fast and the manipulation is easy for the doctors. So we think that the robotic minimally invasive surgery is good for both patients and the surgeons. And this graph shows the market for surgical robot. This is a prediction of surgical robot market of the system, instrument, and the service. And it keeps increasing. And also in Japan, more than 350 Da Vinci, I think this data is a little bit old, but a lot of Da Vinci has been installed. And even in 2016, more than half of the cases of prostatectomy were performed by Da Vinci. I think that some prostate cancer surgery, more than 90% have been performed by Da Vinci. So now robotic surgery is everywhere. And also, Da Vinci is the most famous surgical robots, but there are many surgical robots clinically used worldwide. For example, this is a Mako Striker for hip joint replacement and also for knee joint replacement. And these are also reimbursed in Japan. And this robot is percutaneous coronary intervention. And this was developed by a company named Colindus. But this was recently acquired by Siemens with $1.1 billion. It's a lot. So, starting a surgical robotic company is not so bad things. And this has been approved by the Japanese authority and also installed in a Japanese hospital as well. And this one is also a famous one called Senhance. This one, Da Vinci is without haptics, but this one is with haptics. And this one is called Hugo system, developed by Medtronic. Medtronic is one of the biggest company in the healthcare industry. And it was a great news for us that they decided to join this surgical robotic market. And there are also some new systems. This is by Aulis Health for lung cancer application. And this company was also acquired by Johnson & Johnson with $3.4 billion budget. And this one is called Sports Surgical System by Titan Medical. And of course, we have also a long history in Japan for surgical robotics. And there are some robots called, for example, this one is a liver field, and this one is for HIFU, highly focused ultrasound for pancreas surgery without incision. And this one is a robot to hold a surgeon's hand, because in neurosurgery, operation can take 5 hours or 8 hours. So they developed a robot to hold their hand. And this one is by Keio University, is to insert all robotic tools from one incision in the belly hole. It's common for this type of surgery is common for cosmetic reason. And Olympus is also developing an AI navigated endoscope system. And we also have a new company called Medicaloid, and they recently announced their new robot called Hinotori. It's kind of Da Vinci, but it's a Japanese original robotic surgery. And Da Vinci, it's everybody knows that it's very famous, and it's famous for its urological application. But this graph shows a trend for the procedure, and you see that the application in general surgery is increasing. I mean that general surgery for lung, or liver, or kidney, etc. And now Da Vinci are considered to be a platform for telesurgery. Telesurgery also has a long history, more than 20 years. Telesurgery was feasible even 20 years ago, but the problem was hardware. It was difficult to deliver the hardware at a local city. But now, Da Vinci is everywhere. So they proposed to combine different pair of Da Vinci to do telesurgery. For example, to have an expert in Tokyo to give advice, and also to have a surgeon operating a robot at the local site. And in Japan, we are discussing a guideline for such a telesurgery using the Da Vinci platform. And now I'm talking a little bit about my own research activity. And I belong to the University of Tokyo and Mitsubishi Harada Laboratory. We have been developing a telesurgical robotic system and orthopedic surgical robotic system, microsurgical robotic system, and also surgical skill assessment and automation. And so I'm very interested in the microsurgical application. For example, this one is by Medical Micro Instruments. It's an Italian startup company. You see, this is a finger. So we need such a small robotic instrument for microsurgery. This one is Musa by Microsure, and this also did first in human in 2020. This one is eye surgical robot, also did the first in human in 2018. So the robotic technology has been introduced in the microsurgical robotic domain. And we have been developing this microsurgical robotic system for microanastomosis using the telemanipulation control. So you see that this square is 1 millimeter, and even an engineering student can anastomose the 0.7 millimeter vascular models. And this task is quite difficult even for expert surgeon. And this one is another robot for eye surgery. Again, this square is 1 millimeter, and this is an input device. And you can see that how smooth the control can be. And the robot is also very small, that's 30 millimeter in length and 100 millimeter in diameter. So it's quite small robot for precise manipulation for eye surgical application. And today I also want to introduce our project called Bionic Humanoids Propelling New Industrial Revolution. It concluded already, but it was a big project. The budget was $40 million US budget. And in that project, we proposed high fidelity dummies equipped with sensors for quantifying surgical manipulation, and also for replacing or reducing trials on animal and patients. And then we also developed the smart arm. It's a surgical robot to demonstrate that the bionic humanoid can accelerate the research and the development of medical devices. So I want to show this video, and I hope you can hear. Can you hear?
No.
No, you cannot hear.
Yeah, but we can.
I think it's not possible
yeah,
with
it's
this
okay.
system.
Can you hear?
No.
No, the video
No.
sound will not be heard. That's an inherent problem with the system.
But you can see the video.
Yes.
Okay. So it's with English subtitles, so I hope you can understand. So this is a summary of our project. So I was a program manager of this impact project, and we proposed to develop dummies to quantify ambiguous sensory information to accelerate the medicine engineering collaboration. So this is a bionic humanoid. Maybe the term bionic can be misleading, but we propose to develop accurate dummies that can replace patient. And this is Professor Ayusawa, who was in charge of the development of bionic humanoid for eye surgery. So this one is called Bionic Eye. In fact, this has been commercialized by Mitsui Chemical. So if you want, you can buy this to study eye surgical robot. So we successfully replicate the membrane in the eye ground, and also the eyeball, mechanical property of the eyeball. So this is he is an eye surgeon, and he's demonstrating the surgery. So using the sclera model that duplicate the mechanical property of the human eyeball, a human sclera. And this is the video of another surgery. It's to remove the membrane on the eye ground, and we replicated the mechanical property of the eye ground. And as he says that in eye surgery, the patient is awake. So you cannot say, oops, or you cannot tell young surgeons that it's a mistake. So it's very difficult to educate or train young surgeons. So he said that the eye surgical model is helpful. And this model is for vascular surgery, for the catheter therapy. We measure the mechanical property of the human vessels, then replicated the mechanical property using the artificial materials. And we placed several sensors along the lines of along the vascular networks, so that the force applied on the vascular wall can be detected. So we put some sensors for ultrasound displacement sensor and also pressure sensor. And he's a surgeon, telling that this model is quite similar to the patient in terms of the tactile feedback. And this model can be used for training and also as well for the development of catheter robot. And this is how we measure the human properties, biomechanical property of the human organs, not only the mechanical property, but also the shapes. And we also developed 3D CZ anatomical models because, MRI or CT are not precise enough to know the exact shape of the nerves or the small structures in the brain. So we think that our models are with the highest definition. This one is a Bionic Brain for the surgery of endonasal neurosurgery. This model was also commercialized by a professor. So if you want to buy, you can get it. And this is a Professor Mitsuishi, and I belong to his laboratory. And we developed robots that can reach the brain tumor through the nostrils. And he's a neurosurgeon, and he is operating. And you see that one endoscope and 2 surgical robots are inserted from nostril to reach the area that cannot be reached with straight tools. So this demonstrates dura mater suturing. The dura mater need to be sutured after the removal of the tumor. And this is another type of user interface for co-manipulation. Okay, so I stop here. Okay, then so this is a smart arm shown in the video. So this is a target area in that skull base. It's very difficult to reach with a straight tool. And we developed a very small tool. This is a DaVinci tool. It's 8mm, and we developed a 3.5mm tools. And by changing the tools, we can use this smart arm for other surgical application like vitreoretinal surgery and eye surgery, and also pediatric thoracoscopy. This is for neonatal patients. And this video demonstrates dura mater suturing. This is the final demonstration of the robot. Then we, thanks to the Bionic Brain, we can compare the performance with this robotic suturing and suturing without robots. And we found that the robots are more accurate and more, not more, but adequately efficient and safe. Yeah.
Speaking something I cannot listen to.
You cannot listen to me?
Ashish, can you listen to?
Yeah, it's okay. I can hear.
Oh, yes. Okay, so
Can
that's
hear?
my problem. Sorry.
Yeah.
I am able to hear.
Okay. So maybe, without presentation mode is difficult, but we are studying the AI toward automation. We can use image processing to detect needles and also tooltips. In microsurgery, you cannot trust encoder information because the deformation of the robot itself can be a big problem. And also we developed, we did use AI to detect the phase of the surgery. For example, now you are grasping and now you are driving the needle, etc. Then we want to provide assistance, for example, to optimize the angle of the needle. This is the angle that the expert holds the needle. So we automatically rotate the left hand so that even a novice surgeon can hold the needle like an expert. Okay, and we are also developing a virtual reality simulator. So this is a virtual reality simulator for the vascular surgery because it's difficult for us to collect real robotic data for AI to learn. So we use virtual reality data to collect data sets or to test our new control. And this one is for microanastomosis, and this one is for eye membrane peeling. And we are also using the reinforced learning to optimize the peeling angle or peeling velocity. And now we have been moving toward the non-surgical applications as well. So this is for pathology glossing robots, and this one is with the collaboration of Japanese Space Agency. We want to send this robot into the space station to perform the animal dissection autonomously using the AI, for example, to observe the progress of the dissection and to automate the robotic cutting. And now it froze. So I think now my presentation is okay. Can you sorry, I think it's almost the end of my presentation. I just want to say we started sorry.
Yeah, we can hear you.
Can you hear me?
Yes,
Still?
we can hear you. Yes, we can hear you.
Okay, there's just one last presentation, one last slide to share. So we recently launched a new project. It's to develop autonomous robots capable of research automation to co-evolve with humans. This is called a Moonshot project, named the Co-Evolution of Human and AI Robots to Expand Science Frontiers. We just started, so nothing to share now, but I hope to collaborate with researchers who are interested in such field. So thank you very much, and I'm very sorry for the technical trouble. Thank you very much.
Thank you.
Thank you, Professor Harada, for your very interesting talk And it was really interesting to look at the bionic humanoids and then to see how you're actually mimicking human properties, human organ and tissue properties, and enforcing them in materials. That's very, very interesting. So thank you for
very
sparing
much.
your time. Thank you very much.
Thank you very much, and I'm very sorry for the troubles.
No problem. It was fantastic. There was no problem at all. So our next speaker, yeah, we have a question for Professor Harada. Are you still there?
Yes, I will
Yeah,
answer
Professor.
the question.
Yeah, can you read the question?
Yes.
Yeah,
Yes, and I will. Does a pure humanoid respond to the insertion of surgical tools like real tissue? Does yes? I mean, what do you mean the respond? I mean, it doesn't have actuators, so it doesn't respond, but the deformation are replicated. I hope that I answered the question. Of course, adding actuators are the next step and more interesting.
Thank you.
Thank you very
Thank you
much.
for your answer. So our next speaker is Professor Kimotoshi Yamazaki from Shinsu University.
Excuse me, can you my slide?
Yes, we can see your slide clearly.
Thank you. My name is Kimitoshi Yamazaki from Shinshu University, Japan. The title of my talk today is Prediction, Estimation, and Learning for Deformable Object Manipulation. My main research field is intelligent robotics. This slide contains videos of some research results, housework, support, mobility support, and the factory automation, and the disaster response robotics. Okay, sorry. I make laser pointer. So can you see pointer? Okay.
Yes.
Yes, as another research is motion planning and task planning are also my research field. Okay. Before getting into the main topic, let's organize object manipulation by autonomous robots. If the robot copes with rigid objects, conventional approach is like this. The robot obtains the object information in real world that then input the results into a virtual world. After that, the robot plans and verifies its behavior in the virtual world, then execute the result in the real world. So here is the case we implemented more than 10 years ago. This is a conventional approach. Okay. Well, this time we consider about deformable object manipulation. If we use a virtual world, it is natural to think of using computer graphics technology. In CZ, fiber and woven structure are simulated. This can be said a forward approach. And we may use this technology. However, problem setting in robotics is different. Robots have to estimate object state from sensor data. This is inverse approach, I think. There are difficulties such as long processing time, low success rate, depending on initial conditions, and so on. It's difficult, but very challenging and interesting, I think. So this slide shows some research results about deformable object manipulation. Up across product without collapsing. And holding and dressing. And here is the cable wiring, putting hanger in the shirts and so on. We have developed various functions and system integration for deformable object manipulation by autonomous robots like this. And sorry, I misunderstand the concept of this workshop, but I will start pretty technical talk from now. From here, I introduce our proposed approach in somewhat detail. First, we conceptualize deformable object manipulation as shown in this figure. Before manipulation, the goal state is given, then a sensor data for initial state are obtained. To realize the goal state, we must plan the manipulation procedure, including any midway state. We refer to this level as a plan scale. Then we carry out the planned procedure one manipulation at a time. So we refer to this level as the manipulation scale. To realize manipulation as conceptualized on the previous slide, we are building a dual level system as shown here. In the plan scale, overall motion plan, including midway state generation, is performed. In the manipulation scale, the cross shape is predicted and controlled by appropriate perception and manipulation, which are online process. Here, we introduce EMD-net. This is a modularized neural network, encode, manipulate, decode network. Here is an example of the planning. Initial state is unfolded rectangular shape, and the goal state is shown here. From these input, EMD-net outputs both manipulation and cross shape. The manipulation consists of peak and release point, as shown in green and red dashed lines. In this case, 3 manipulation steps were automatically generated to obtain a shape that is similar to the given goal shape, like this. For the manipulation scale, we assume that the initial state, final state, and the initial trajectory are provided by the plan scale. We aim to solve the manipulation scale using 3 core functionalities: shape estimation, shape prediction, and trajectory correction. The accuracy, flexibility, and execution time of these 3 functions must all be at practically applicable levels. Core features of our approach are that we use a mesh format for cross-shape representation and run a forward model of the object dynamics for real-time shape prediction. First, I will explain shape estimation. The goal of shape estimation is to reconstruct the cross shape from a 3D point cloud. Our approach is to generate a cross mesh that is consistent with both the observation and the non-cross topology. I will explain the procedure step by step. First, we obtain 3D point cloud data, SPC, from the sensor. Then we convert the point cloud into a voxel representation. At this time, we boost Z coordinates to capture more than height detail, such as cross wrinkles. Then we estimate the cross shape probabilistically using the voxel to mesh network. We call this V2M net for short. The input of the V2M is the voxel representation, and its output is a probabilistic cross mesh. The probabilistic mesh format describes vertex positions as 3D multivariate normal distributions. Finally, we derive a deterministic estimate using a topological refinement procedure. By minimizing the vertex positions, negative, we ensure consistency with the observed shape. And by minimizing a topological loss, we improve the realism of the estimated shape. Next, I will explain trajectory correction. The goal of trajectory correction is to make the manipulation outcome S sub n match the goal shape S star. To achieve this, we predict the outcome and adjust the trajectory so that the prediction matches the goal. Formally, we minimize the objective function shown here. The shape prediction is performed using a deep neural network trained as a forward model. The network architecture is shown here. The encoder and decoder map meshes to latent space and back. The LSTM module predicts the shape evaluation, for a given trajectory. Here, you see how we predict the full shape transition for a given manipulation trajectory. And we correct the trajectory by minimizing the loss between predicted outcome is sub n and the goal shape is star, like this. Next, I will explain the flow of the manipulation process. First, we initialize the manipulation trajectory and estimate the current cross shape. Then we start the manipulation. Manipulation follows the following procedure. First, we predict the final manipulation outcome and calculate its error relative to the goal shape. If the error is above a threshold, we trigger trajectory correction, devising the trajectory to reduce the error using back propagation through a prediction network. If the error is below the threshold, we execute the next n frames of the manipulation and obtain a new estimate of the resulting shape. By repeating this procedure until all waypoints of the trajectory are passed, we manipulate the target object into the goal shape. I will introduce our experimental results. We evaluate our method on a cross-folding task. We first evaluate all three functions in simulation, and then test the integrated system in hardware experiments. Our dataset consists of over 3,600 manipulation sequences generated using the ArcSim simulator. This slide shows the trajectory correction results. The evaluation conditions are as follows. We initialize the trajectory as an arc-shaped curve. The grasp points are defined by the initial trajectory. We evaluate three test scenarios. In scenario 1, manipulation proceeds undisturbed. In scenario 2, friction is lowered, causing the cross to slip during the manipulation. In scenario 3, an external disruption is applied partway into the manipulation. The figure and animation in the middle of this slide show an example of the manipulation with correction. We observed that with correction, the trajectory was modified appropriately in response to the external disruption. With correction enabled, the error is about 5% of the cross size. The time cost for trajectory correction depends on the number of frames, taking 9 seconds for 50 frames and so on. Finally, I will show a result from our hardware experiments. We used the dual-arm robot Hero. The cross-shape data was obtained using an Azure Kinect RGB camera placed in front of the robot. This diagram shows a unified system combining a plan scale method and manipulation scale methods. Okay. Using the system mentioned in the previous slide, the robot solves a folding problem from the initial state to the goal state. The left bottom movie shows the first manipulation, like this. Okay. Then the right bottom shows the second manipulation. Okay. So this shape is similar to the target shape, as you can see. Okay, I conclude my presentation. I talk about deformable object manipulation by autonomous robots. Especially, I introduced a framework integrating shape estimation, shape prediction, and trajectory correction. As a future work, I need a deep understanding of deformable object manipulation. Then we have to propose and verify the methods suitable for autonomous robots. That's all. Thank you very much.
Thank you, Yamazaki Sensei. It was a very interesting talk, technical talk. So we have a lot of students and researchers also in the audience. So it's very good for everybody.
Thank you.
Thank you for your interesting talk. It's a difficult topic, modeling deformable material. That's a difficult topic, actually. So thank you for your talk again. Our next speaker is Professor João Venture of the University, Tokyo University of Agriculture and Technology and AIST.
Okay, so thank you everyone for inviting me to this first Robotics Society of Japan and India Society, Robotics Society workshop. I'm really very pleased to be here today, and I would like to introduce briefly some of the activities that we have at Tokyo University of Agriculture and Technology, not to be mistaken with Tokyo University. One of the activities, like one of the subset of the activities in robotics I would like to talk about are mainly human dynamics research. So I'm a professor at Tokyo University of Agriculture and Technology. I'm also a cross-appointed fellow with the National Institute of Advanced Industrial Science and Technology, which is called AIST, for those that are familiar with it. And actually, Tokyo University of Agriculture and Technology and AIST have a partnership agreement. And so AIST, which is a governmental research center, also hosts students from the university to do research in their facilities. And in the Department of Mechanical System Engineering, where I belong to at the university, we have several labs that are working in robotics or affiliated robotics, kind of close to robotics field, and also in human body dynamics, like rehabilitation and this kind of research. So we have two big labs working on mobility. One is the lab from Professor Santanu, who is working mainly on what is called like smart mobility, so like self-driving vehicles and assistance to drivers. We have here a number of fully equipped like regular cars, mini cars, and different equipment to like do research on these aspects. And then there is another lab who is also working on mobility and driving mobility, who is Professor Morris' lab. But in his lab, they are more interested in drivers' behaviors and how to correct driver behaviors to get better at driving and to avoid, of course, traffic accidents. and also eventually to assist drivers, but to study the effect of assistance on drivers. So it's really working at the boundaries between the machine and the human, or the machine and the human interface, really. And then there is the lab of Professor Mizuchi's, who is working on many, many different research topics, but one of his main interesting research topic is probably the development of humanoid robots with musculoskeletal mimicking systems. And this is one of the examples here. This is work that was actually started at the University of Tokyo in the lab of Professor Inaba. And this is something that has been continuing on and on. And the idea is like how to control these like super redundant systems and how to make the robot move, but also trying to make some kind of like artificial intelligence inside of the robot. So again here, because of the nature of the humanoid robots and the imitation of the human, we're really at the boundary between the human and the robots. And in Professor Tanaka's lab, here we are really much interested in the research of human movements. So how human performance and human movements can be evaluated, and in particular in the case of like sports and rehabilitation. And then in my lab, also on human control and on like human motion analysis to try to understand what is the link between the robots and the humans and how they can work and live together, which was one of the point that was in the introduction talk of the presidents of like the Indian Robotics Society, which really is like how to live and work together with robots. And at AIST, we have also 3 labs that are inviting some of our students and work with the students from Tokyo University of Agriculture and Technology. One is the lab of Professor Ayusawa, and his work is really very close to mine, actually. I co-supervised his PhD thesis and his master thesis when I was at the University of Tokyo. He is working on studying human movements and how to reproduce these human movements into humanoid robots as one of his research topics. Professor Sagawa's lab is also working in trying to measure human movements from video images, so to create 3D models of like very precise 3D human models from video images, and then to try to use these video images and this human like motion tracking for further motion analysis. And then one other of the researcher that is working with us is Professor Yamanobe, and Professor Yamanobe is working in like the verge between manipulation and industrial robots and also human robots cooperation. So the idea is to try to understand how human and robots can collaborate together, and when human and robots have like a task to achieve together, how can these tasks be done without having the human like scared by the robots, or the robots always just following the human. So there's really a need for collaboration here. And so that's like the main labs that we have at Tokyo University of Agriculture that are dealing with robotics. And I wanted to introduce you very briefly some of our research activities that are very much related to like many of these labs. And it starts with dynamics. So again, this is going to be a little bit maybe technical, but just very briefly. So the idea is to really work with the equations of motion, and you should see an F here, but it's cut here. So this is the external forces actually. And this equation of motion works for any kind of multi-body system, whether it's for car, trucks, robot arms, humanoid robots, and of course, for the human. And the idea is like, how can we use this equation of motion for the human? And in particular, how can we have access to dynamics information? So the idea is to use movement. So basically, we need to be able to measure the movement of the system in the 3D space, the movement of each individual parts of the system with respect to each other, and then we eventually need to be able to measure forces. And if we have access to this information, now actually this is very easy to have access to this information. We have multiple sensors that can do that. Either it's like very expensive lab-grade motion capture devices, or as presented previously also by Professor Yamazaki, we can have access to Kinect, small IMU sensors, smartphones, and very cheap force sensors. And then with this information, we can actually calculate the dynamics properties of the system. So for example, we can measure the mass, the inertia, the tensor of inertia, and the position of the center of mass of the first moment of inertia. And these can be applied to many, many different types of systems. And in particular, we can apply it, as I said, to robots, but we can apply it to humans. For example, if we have human jumping in the air, we can actually use this kind of compact equation where we can find the dynamics of the human while it's jumping in the air. And we apply this technique to patients with post-stroke, in post-stroke rehabilitation, and we can track, for example, how their rehabilitation process is doing by comparing their paretic side to their healthy side and see if they're regaining muscle mass and if they're regaining their motion abilities as well. And so that's really a tool that we have been using with the National Rehabilitation Center here in Japan to try to understand how inertial and mass properties are linked to movements. Another application that we have been also doing is to take it the other way around. And with human, when we're trying to do dynamics identification, we need to do something that is usually called data maximization, or my video seems to be stuck. Okay, whatever. So data maximization. So we need to guarantee that we have enough data, because this is a data-driven model. So we're not doing machine learning or deep learning here. We're doing model-based system identification, but this is still a data-driven method. So we need to acquire a rich enough data set that has enough information to drive the model to converge or to get a results that is actually relevant and generalizable. And looking at what we did with the human, we actually created a similar way to generate systematically optimal exciting, we call this dance, because it looks like the robot is trying to dance, to actually maximize the number of data points and maximize the quality of these data points so that we minimize the error on the identified values. And so we have a robot that can generate by itself fully all the movements, and the algorithm takes into account balancing problems, self-collisions problems. And so the robot just stand on one foot, then move to the other one, and just generates all the movements that it requires to minimize the error on these dynamics parameters that we want to identify, for example. And some of the application of these models, when we have precise models, is, for example, to get rid of the force plates, because we need to have access to the force information. But in many of the rehabilitation settings, actually measuring force is quite a problem. And in particular, in multi-contact conditions. So for example, in sit-to-stands exercises for rehabilitation, in these kind of systems, we have contact at the end, contact at the buttock, and contact at the feet. And we need to calculate how much force is on each of these contact points. And with the very precise models that we have, so basically we have a regular general dynamic model. We do the personalization with the appropriate dynamic parameters. Then we are able to actually contact the wrench, the external wrench at each contact point for different conditions. And so this is an example here where we're doing here the data maximization. And then once this is done, the person is going to do some sit-to-stand task here. So basically standing up and stand to sit-to-stand and stand-to-sit tasks, which are tasks that are often used in rehabilitation. And so that's basically some of the results. If we compare the forces that are measured, so we can see that we have a fairly good ground reaction force estimation in all the directions, even if they're like sometimes very small. And so we are fully equipped for full body dynamics analysis and for robots and humans. And so the next thing that we've been interested in is to try to generate like novel models and to classify models from forces. I said that forces might be difficult to measure in rehabilitation settings, but on the other way around, forces are quite easy to measure when we are sitting on a chair during the whole day, or we are seated on a chair on a wheelchair for our whole life. And so we've been using force measurements to do classifications of motion, so motion recognitions and motion evaluations for like sports activities. And we've been using it for like different types of exercises. We've been using it for baseball, pitching, evaluation, but we've also been doing it for wheelchair-ridden activity recognitions to try to provide feedback to patients, to therapists about wheelchair-ridden patients, and about their activities during like the whole day, during the whole week, during a whole month, about the changes in their behaviors or the changes in their movements. And also we are coupling this with assistive devices. So we're trying to develop new devices for people with muscular dystrophy so that they can have access to robotic arms that can adapt to their behaviors and improve their quality of life. And so I think I went very, very quick, but I would like to really thank you again for this opportunity to present our activities here. And I want to thank all my students and my collaborators and the funding agencies that are supporting our research. So thank you very much for your attention.
So thank you, Professor Jean-Pierre. So very interesting talk on identifying human dynamics, which is a difficult topic actually. And yeah, a lot of technical stuff, which is very nice for the students. So thank you very much for sparing your time. So we are running a little late, but maybe we can take a break for about 10 minutes, if it's okay. So we'll take a break of 10 minutes. I think it is 10:45 in India. So we'll meet at 10:55. In Tokyo, I think it is 2:15. So we'll meet at 2:25. Okay, so we'll be meeting back at 2:25 Japan time and 10:45 Indian time. So
55.
Yeah.
55, yeah.
So the second part of the workshop, we have the talks from the India side. So we have 4 speakers from India side. Professor Subir Kumar Saha from IIT Delhi. Professor Asokan T from IIT Madras. Professor Ekta Singla from IIT Ropar, and myself, Ashish Dutta from IIT Kanako. So we start off with Professor Subir Saha. So please keep your talk to within 20 minutes. Yeah, Professor Saha.
Yeah, so good morning and good afternoon. Konnichiwa minasan. So this is a nice opportunity to meet many of the Japanese colleagues as well. Particularly, I remember 2010 when I met Professor Shibata with the request from Professor Ashish Dutta to initiate a dialogue of the Robotics Society in India, and now where we are. Thanks for the continued support from the Robotics Society of Japan. So the title of my talk today is Robotics, Robotics to Robotics actually. I'll tell you why it is like this at IIT Delhi. So I'm a professor at the Department of Mechanical Engineering and acting as a project director of a new non-profit company at IIT Delhi. And on the right hand side, the logo, we are celebrating 68 years. So to begin with my experience, as has been directed by Professor Dutta, is to talk about robotics at IIT Delhi. So my experience with robotics at IIT is from 2001 when I started the mechatronics laboratory here. I just wanted to show you a device a simulator which we have done as a truck simulator for our Indian Army. So this manipulator, the motion platform, which is basically a sphere platform, is a very popular device used as a flight simulators. But here the target was a truck simulator. So complete kinematics, dynamics, motion planning was done at Iit Delhi. Later on, it was taken to the site in Hyderabad, which is kind of south of India, and we did the integration there. When we were developing that truck simulator, which was about 1 ton payload capacity, we are also playing with these kinematics to understand the control and other aspects. So we developed a small device for which we later found an application by our professor in biomedical engineering for etching implants. So you can see how the laser spot has to be traced along the implant. So a nice offshoot application, and now this is so cute and so useful for the education. We are making it available for the other researchers outside Iit Delhi as well. Then comes 2010. We had a sponsor program from our Atomic Research Center at Mumbai, and we created a program called Program for Autonomous Robotics, and that was another program which was led by Professor Santanu Chaudhury, whom you met in the morning. He was a faculty at Iit Delhi, and he was leading this activity where about 12 faculty and 20 students were taking part here. And we have developed several technologies. I will show you maybe 1 or 2 glimpses here. And as a part of our annual workshops, we also planned the Robotics Society that time onward. So we are very obliged to Robotics Society of Japan as well as this project, who has actually led to the formation of this society. So this is one of the tele operations in an immersive environment. So please watch the video. So we are using a haptics device, as you can see it, to manipulate a robot which is a little farther distance here on the top right. And actually, we are trying to control the virtual robot, which is at the center of the screen, and then to take care of the delays. These kind of things have been attempted, that whatever control is done to do the virtual robot, the same signal goes into the real robot which is behind. So now we are trying to adopt the technology, even though it was for nuclear at that point of time. Now we have a very strong medical activities beginning here. I will share a few concepts or the slides later on. Then in the manufacturing setup, assembly setup, we have this force following robot. We know the robots are typically used in cages, so we wanted to make the robots as a human friendly. So we are trying to take care of the current passing through the motors to have this kind of flexibility implemented. And this is 2 industrial robots, put it in a master slave manipulation mode, and finally understanding various aspects of the compliance in the robot. So we attempted the peg-in-hole operation by introducing a force-struck sensors here, so that we can trace this circular hole and then determine from the force plots that what is the center of the hole based on the resistance coming, and then insert the component. Now the C part. Last year, or in 2019, there was a call for a proposal by our government of India to start the technology innovation hubs at 25 institutes in India. And they have to form a Section 8 company, which means a non-profit company. So we have been assigned to work on the area of collaborative robotics based on our experiences and the proposal submitted. So this is our website. It talks about various activities, the research we are trying to conduct, the kind of online courses we want to do, the kind of international collaboration. I am happy to some of Professor Shibata and other professors have shown agreement to work with us, even though we have not really started anything concrete. Maybe we should do it. 170 crores rupees means about 20 million US dollars for over 5 years. And we have about 100 people coming and interacting with us. And these funds are available for international collaboration as well, except that hard cash cannot be sent to the foreign land, but the foreign professor can hire an Indian student or Indian researcher in India for whom the payment can be made from our company. So what we are working presently is, as per the research is concerned, other than the skill development activity, so we have classified 50 plus interest from the professors into several categories: Industry 4.0, intelligent and secure communication, drone applications, rehabilitation robotics, healthcare robotics, medical simulators, human-robot interaction. So two of the panelists here are actually helping us. Professor Ashish Datta will be helping in the rehabilitation robotics to lead the team of 8-9 projects around the country, and Professor Asokan will be helping us in the medical simulator as the leader of these things. And we have human-robot interaction. We have one professor from Japan, from Shibata Institute of Technology. Professor Matsuhira has shown keen interest to work in this team in order to provide the robotic technologies which they are working on. As I said, no money will be transferred to him, but if he comes to India, we take care of. If his students want to come, we take care. Similarly, when the people go there, that is the way collaboration happens. What has impressed me in the lecture by Professor Harada is, we are thinking of medical robotics center in our off-campus, which is about 50 kilometers from here, to impart training and R&D related to medical surgical robots. And this would be, one of its kinds in the country, and we would like to take a lead through this company by investing maybe the simulators or possibly the buying one robot if possible, whether Da Vinci or CMR or some names also mentioned by Professor. So we would be very keen to see collaboration with University of Tokyo in terms of medical robotics. One just demonstration I wanted to show, which we have begun as a part of this activity, is tele-ultrasound to be carried out. So this is the same haptics device as you've seen at the beginning. So we have a cobot from Universal Robot, as you can see here, and here a volunteer. So the USG, the ultrasound probe, is a 3D printed because some testing of the algorithms are going on. And this is in the factory setup. Later on, it was taken to the hospital, and about 20 plus volunteers have been tested, and they have given their feedback. And we are now in the next phase of improving it, in terms of the design, the orientation, and the doctor's comfort, and so on and so forth. And this will help us in not only for the COVID situation, but post-COVID also, take this kind of healthcare diagnostics to the remote places in the country as well. This is just to mention that in India, particularly at Iit Delhi and other institutes, we have to put a lot of emphasis in terms of education, because we have a large young population. So this is my contribution towards that. This book, this is the second edition, the white color, and the green is the first edition. In order to assist helping the students to grasp the subjects well, like the kinematics and dynamics, we have a software called RoboAnalyzer, and Rajiv, who is helping in this workshop, has been my master students, now a faculty. He is the key driver taking care of this software. Just to show you a glimpse of how this software works. This is a priceless software, can be downloaded free of cost. And starting from understanding what are the DH parameters are, right, and the forward kinematics and the direct kinematic, inverse kinematics. For example, this is just a two-link arm. Now, if you wanted to understand what is the forward kinematics, so this is the way it looks. Then we have a virtual robot toolbox, which has about more than 15 plus industrial robots, taking all the standard KUKA and Kawasaki and all such things. Then we have an inverse kinematics module, so here is the virtual robot module, for example, ABB, IRB. It gives you some basic information, and then you can run in, joint control mode, or you can give a Cartesian control, so you can say start, and you can see how it is moving. And this is the end effector configuration, the position, the orientation, and the homogeneous transformation. So this is a more than 10 years old kind of software. We are improving every month, you can say it. This I will show you. I skipped this page. So that was about our laboratory activities, and then our educational part. But then education, in Japan, I know Professor Matsuhira sends every year some students on the project-based learning. So you have a lot of emphasis. In a similar line, what I call is the competition-based learning, not the project-based, because project-based, the zeal of the students to win something is somewhat lacking. But if it's a competition, they know they have to win. So Robocon, again, Japan originated contest by NHK, started in 2002, the international competition. I've been strong supporter of this thing. 2019, we hosted at Iit Delhi, and 2022, we'll be hosting in India, the ABU competition. And just a glimpse from here. So 2019 competition was held in Mongolia. So generally the theme of the game is taken from the country which hosted, like 2022 will be from India. Okay. And you can see the kind of challenges thrown to the college students, they are enormous. Like as you can see, this is a working robot the students have to build. So to me, this includes all aspects of engineering which are typically learned in an undergraduate course, and that would give a lot of motivation to the students, to learn what next. So that's the way we try to preach this thing very strongly. And in order to reach to the masses, we wrote a small fiction book called Rugby, Robotics Competition Knowledge-Based Education and Engineering. No equation here, just a story form. So you can see how the robots are moving. So all aspects of engineering, from concept to design to manufacturing to debugging, and at the end, the strategy, the robot which you see in front of you, has been the very popular team, but the other team which was not so popular in the final, it won because of its strategy. In order to emphasize this aspect, the reliability and robustness to the young kids or the young students, so we said, okay, after Robocon competition, what next? So 2009, we started this journey by saying that, okay, if I keep the robot for 24 hours unattended, what happens? So as you can see, in those days, we were following lines. So line following robot, So we tested the electric circuit reliability, the robustness. That okay, after 7 days it was getting burnt out and stuff like that. And this is 2019. We made it autonomous, as you can see in the right hand side. And for your information, as you can see here, IRIX 2019 in collaboration with Matsuhira, this robot was has a communication from the exhibition site in Tokyo to be able to control. They could not control the robot, but certainly they could successful. Quite nice collaboration. However, journey continued, and then 2019, the same year, Robomus 5, that another version of this robot has been adopted by a company in India called Peer Robotics, and he claims that this is the true collaborative robot, as you can see in this video. And so the base you can see it's the same Robomus 5, and then you will see towards the end. Oh, okay. I just wanted to go fast forward. Let's see if I can go fast forward. Yeah. So here you will see someone is coming and trying to push, but then he will not put all his forces here. Okay, let him. So you can put it in autonomous mode. You can put it in a collaborative mode. So this is still in autonomous mode. Now I think it is switching to collaborative mode. So the guy picks up the boxes, and here collaboration comes. He's not exerting his whole effort. He's just showing the intention, and the robot is timing. It's like a power steering system. So we have several other companies. There is one drone company in the campus. In fact, tomorrow they are going to demonstrate with the 50 drones a formation of ships. So it is a challenge they have taken for the entertainment and farming aspect. This is our Iit Delhi campus. For those who could not visit yet, have a very brief glimpse. So this is an advertisement. We're doing it for our Diamond Jubilee celebration last year. And this was on Independence Day, the 15th August. You can see the flag hoisting activity happening there. Yeah. There is one more company, Vectros. So we interact with these startup companies to this. And in order to emphasize the skill development, so in India we have the largest young population in the world. So we do take care of a lot of skills. So on my personal note, along with some collaborators, we have started a competition with the Tejpur University, which we call self-driven, self-learning, and self-evaluating. So there will be a paper in this conference, and this is some slides from there. For those who are interested, can attend that session. So with this, I conclude. I talked about mechatronics. I talked about RoboAnalyzer software. I talked about Robocon as an experience of skill-oriented learning, which I also call it as an innovative teaching mechanism, and ROC, RoboAnalyzer-based competition, as a skill development activity. Acknowledgement to all our friends, students, spouses, and thank you very much for your kind attention. And I'm there in the session till 1 o'clock. So if there are questions, please feel free. Thank you very much.
Thank you, Professor Saha, for your wide-ranging talk covering research and student activities and the software developed at IIT Delhi. So our next speaker is Professor Asokan T from IIT Madras.
Hear you. I think there is some issue.
You're not able to see?
if you are using Firefox, Mozilla, maybe can you
Yeah.
please share complete screen?
I have shared complete screen actually.
Yeah, but when we lost your audio when you shared.
Let
Can you
me
please
try
try it
again.
again? Yeah. I think we are not hearing you.
Okay, but we can't hear you.
We can't hear you. Sir, we had this issue earlier. Can you please try from Chrome? Google Chrome.
So I need to choose that link, right? Okay. The
No,
link which is
you will have to exit from here and then again join using Chrome.
yeah, but I tested this. It was working. I mean, before we started the program. Anyway, so you want me to go back, go to
or you can try a particular window and see whether it works. Share only one window.
Okay.
In the pop-up, there will be full desktop window tab. So maybe you can try only window.
I'm not able to see those files here. In the select window option.
No, you open that PowerPoint. It will be shown.
I have opened it, but it's not coming. I have get only the entire screen option.
Oh, that's
do it last time it came, no, correctly.
No,
yeah, when I opened it came actually. So my screen is. Can you hear me now?
Yes.
Okay, so I hope things works now. Is it okay now?
Yeah, okay.
Oh, good. Yeah, good morning, everyone. Good morning and good afternoon to all our friends in Japan. First of all, thanks to the organizing committee for AIR for this workshop and giving me an opportunity to speak about the robotics research at IIT Madras. And for our friends in Japan, IIT Madras is actually situated in the southern part of India, Chennai. So we are adjudged as the best engineering institute in India as per our Indian ranking for the last 4 consecutive years. So I'll be presenting a brief about the research in robotics, primarily happening in the institutes. So I'll be talking about the underwater robotic research, where we do the design, dynamics, and control of autonomous underwater vehicles. That includes the underwater robots, glider, etc. I'll be briefly talking about the work in aerial robotics, where we work on the design of aerial robots as well as on the path planning and control of aerial robots. Then briefly talk about medical robotics, where we are looking at the design of surgical robots, especially the teleoperated surgical robots. And as part of this, we are actually working on this hand tremor compensation and strategies for identifying fatigue-induced tremor, etc. And then I'll be talking about some special design of robotic systems, which is primarily a mobile manipulation, which is different from the conventional mobile manipulators. I'll talk about how the design of mobile manipulators can be made simple, but at a bit robust and less complex. And apart from that, we have faculty working in the area of RL and ML applications in robotics. So I don't have any slides on that, but we have a few faculty who works on the learning aspect of learning aspects and how these learnings can be used in robotics. So let me talk about this underwater robotics research. So I was involved in the design development and control of a 6 degree of freedom autonomous underwater vehicle. So as part of the research, we looked at the modeling and the simulation of underwater robots, 6 degree of freedom robots. So this robot is quite big. It's actually a commercial application purpose. though it's not commercially available, but we were developing it for a 300-meter depth with around 15-meter length for the robots. And after understanding the dynamics, we designed the control strategies for the robot. So we came up with the different control strategies based on the requirement of the particular vehicle. And we developed these strategies for path planning. So we came up with a new method called improved line of sight method for path planning, where the normal line of sight method cannot be applied in underwater robotics because the robot has to just go on the just above the sensor to collect the information. So any approximation or any path away from the sensor will be not useful. And therefore, we came up with this method called improved line of sight methods. And apart from that, we came up with a methodology for the obstacle avoidance also. So this obstacle avoidance strategy is different from the conventional method. So we actually came up with a multi-point potential field method in order to increase the safety of the robot itself, because the robot should be protected from hitting any objects in the water, floating or stationary or moving object. So we came up with an improved method called multi-point potential field method. So this was and this has been published. And what you are seeing on the video is the first sea trial of this robotic vehicle. You can see that it is being deployed from the ship, and once it is deployed, it is fully autonomous operation. So once it is commanded to move underwater, then of course it will go as per the designed paths, avoiding the obstacles and following our improved line of sight method. And after that, we can collect it from the targets. This was the first trial, so very limited capabilities were tested, and this work is still going on. So we are trying to improve the navigation and control aspect of these robots. As part of the underwater robotic research, we came up with a new method for buoyancy variation. So most of the underwater systems use the weight change as a buoyancy method. So they pump water inside or they pump water from the vehicle to change the buoyancy, which actually is a bit problematic because of the seawater corrosion and all other issues. So we came up with a method of volume control, where the volume of the whole vehicle will be changed so that there will be a change in buoyancy. So as you can see here in this figure, so what we are using is the bellows. So the whole body of the robot is made up of metallic bellows, and there are electric motors inside, and these motors will actually try to compress or expand the bellows. So you'll get a change in volume, and whenever the volume changes, there will be an increase in buoyancy, so it will start going down, and then when you try to change the volume again, this will come up. So this way, you will be getting a sinusoidal motion for the glider, and the power required is very less in this case. You don't need to have a thruster to do this. And what you are seeing here is actually, okay, there is a video. So this is the fabricated prototype, and then finally we tested this in the swimming pool to show that it actually works. The buoyancy variation is working. So now we are actually converting this into a commercial product. So we already set up a company to commercially develop this product and then use it for commercial application. Just got high endurance because of the power requirement is very less, and it is very silent. There is no thruster, so there is no disturbance to the surrounding medium. So we hope that this can be commercialized in a short span of time. And the second is on the medical rehabilitation robotics. So Professor Kanako explained about the surgical robot and the importance of surgical robotics in the current era. So we actually designed a surgical robot with two master arms of 7 degrees of freedom and two slave arms of 7 degrees of freedom, with capabilities for haptic feedback and a 2D vision system also. So we have a camera arm which carries the camera inside the body, and then these two slave arms, as you can see, these are the two slave arms which will be carrying the surgical tool, and then we'll be able to control this using a master robot, as you can see here. I'll get the details later. So this is the system diagram. You have the surgeon console where the surgeon will be sitting and then watching the video image, and then he'll be controlling the two master arms, and that master arm motions will be captured and it will be processed in the controller, and it will be passed to the slave robot. The slave robot will be manipulating the surgical tool. So this is the surgical tool we actually designed. This is our own design, a patented design. So as you can see here, we have 4 motors to control the tool tip, 4 degrees of freedom at the tool tip, and this part will go into the human body, and then the tool tip can be manipulated using the master arm. And this is the final design for the surgical toolbox. And this is the master robot. That will be having 3 degrees of freedom for positioning and 3 degrees of freedom for orienting the tool. So the surgeon will be holding on to this gripper. And again, we have a patented gripper design, which will be used for controlling the tool at the surgical site. So we have 2 such master arms. And then, of course, these motors will provide us, help us to provide the haptic feedback also. I'll just show you the video. The video of the whole system. So this is the master robot, which will be, so you can see the person is holding onto the grasper, and it has got all the 6 degrees of freedom, plus the grasping degree of freedom. And all these motions will be captured using the encoders, and then you can find out the actual Cartesian motion of the tool tip, sorry, the grasper, and that will be passed to the slave manipulator. So you have 2 slave arms. So this is the laboratory prototype, so it may not look very very nice here, but of course, if you change, when we convert this into a commercial product, we can actually make it much more attractive. So this is the slave arm with a remote center of motion mechanism for getting the trocar point as the point of insertion. And then we have this tool, the surgical tool, as I mentioned. The surgical tool will go into the human body with all the 7 degrees of freedom possible at the tool tip. And this is the master slave manipulation. So you have the master robot is being controlled, and the video image will be appearing on the screen, and then you can actually see that the slave robot will be manipulated, or the tool can be manipulated as per the requirement by the operator. So this is a complete master slave tele manipulation. So the tooltip transmission is through cable. So you can see that the motors are all at the distal ends, and only this part will be inside the body, and you can have very fine manipulation of the tool at the surgical sites. So we are now converting this into a commercial product. So through that, with the help of the Technology Innovation Hub or the Robotics Center at Iit Delhi, we are planning to have a commercial product designed and developed in the future. Just to show you that we have actually worked on do some active hand rehabilitation work also. So this is a simple device with a control with a single motor for controlling the fingers. So those who are having difficulty in moving their fingers because of some neurological disorder, so this device can be used for controlling the fingers. So now, depending on whether we want to have it as a remotely operated, or it has to be a program, so both are possible, or we can want to use the other hand as a control device. So there are multiple possibilities, and again we can actually develop this in a commercial way at a later stage. Okay, and the other important work what we have taken up in the recent past is the design of multimodal robots for field and industrial applications. So multimodal robots are the robots capable of doing multiple modes of locomotion, grasping, and manipulation. As you know, any manipulator, any industrial mobile manipulator requires to have the capability of mobility, manipulation, and grasping. So these 3 things need to be there for any mobile manipulation. And most of the existing or industrial commercially available mobile manipulators will actually a combination of these 3. So you'll be having a manipulator, you'll be having a mobile platform, and then you'll be having a grasper attached to it.
Did we lose? We have lost him, it looks like.
Professor Ashokan, can you hear us?
Can you hear me? Hello?
Yes.
Hello?
Yes, we can hear you.
Hello?
Yeah, we can hear you.
Hi, Ashish?
Yeah, we can hear you. Can't you hear us? Are you muted or no, you're okay.
Can you hear me?
Yeah, we can
Yes.
hear you.
So you can continue, sir.
Yeah, you can continue.
Can you hear me?
Yes, we can hear you.
Hello? Ashish, can you hear me?
Yeah, I can hear you. So please continue.
Oh, sorry. Yeah. Okay. There was some problem, I think.
Yeah.
Okay, so I hope I was explaining about these multimodal robots, and we are actually trying to design a novel multimodal robotic platform which incorporates grasping, manipulation, and locomotion. I'm getting some echo.
Yeah, you can continue. We can hear you.
Okay, fine, yeah. Okay, so the design concept for the multimodal manipulation is that we will be using the conventional, for the concept of conventional manipulation, then we'll be using the grasping mechanism. But what we are trying to do is to combine this into a single unit and then get the manipulation capability. So as you can see here, the main design concept is basically these two graspers. So you can see there are two graspers
Full
which are
screen mode, presentation mode.
Yeah, I'm in presentation mode. Can you see?
Okay,
Yeah, you
we
can
see.
continue, please.
Yeah, no problem. Yeah.
Yeah. Okay. So the main design concept is here. There's two graspers. The graspers can act as a grasper, a manipulation device, as well as a locomotion mechanism. So we have two such graspers, and these graspers are connected through serial linkages. Now we'll be using this as a mobile robots capable of manipulation, grasping, and locomotion. So how we get this? So we can actually use this these two graspers. So when it is in this mode, it can actually stand on one leg and then do the manipulation, or it can actually stand on both the legs and then have a rolling motion or a walking motion. And we are using the same motors for all these activities. So this is the grasper design. So as you can see here, this grasper is especially designed with the two jaws, and each has got the 4 sheaves, and there is a belt drive. And by properly controlling these sheaves and the belt, you will be able to have the grasping. You can have a in-hand manipulation, or you can just have a grasping, or it can be used as a wheel for locomotion, or can be used as a leg for walking. So these are the capabilities that we have in this design. So I don't go into the details of this design. Let me show you the capability. So this is where actually we can use it for the object manipulation, or the object can be fixed and it can be used as a simple grasper also. So both the in-hand manipulation and within-hand manipulation can be done using the grasper. And how is it done? So as you can see here, this is the first prototype of this robot. So you can see here, this is the these are the two graspers, and they are connected through the linkages.
Asokan,
And,
your slide
this-
is not changing.
Oops. It's not changing now?
Slide number 15, but not in full screen. Yeah, now we see slide number 19.
Yeah, that is the one I am using. Okay. Yeah. So can you see the video?
No, sir. We are still looking at the PowerPoint, which has left side preview and then the slide. Maybe within this you can play. Come out of
Oops.
slideshow.
Yeah.
Yeah, here only if you can play.
Yeah.
Is it visible?
Yes.
Yeah. So this we can see that now it's actually in a wheeled locomotion mode. And this mode can be changed to a grasping and locomotion. So you can actually hold an object and then do the locomotion. So you can do the object manipulation, grasping, and locomotion. So that is the first mode of operation. And then we modified this to get the next one is the brachiation motion. Or brachiation is that hold one object and using one grasper you can hold, and the other grasper can actually actuate it to hold on to the next object. So we'll be able to get a brachiation motion using this mechanism. So grasping and brachiation can be achieved using this method. And the last one what we can do is with this is the walking motion. So you can actually make this as a walking mode. So in walking mode, what we do is that we'll allow the robot to stand on one leg and then change its center of motion. And by controlling the motion of the center of motion, another leg, this leg can actually be moved to the next position, and then we can have a walking motion for this. So both all the locomotion modes of rolling or wheeled locomotion or walking or brachiation can be achieved along with the grasping capabilities also. So the grasping, manipulation, and locomotion capabilities made into a single system. So this is finally further being developed to get a full walking motion. We are still in the process of developing it, and we see that this can actually, once we develop this in a full product, there will be a lot of utility for it in the industrial applications. So moving on to the next product or the next topic, which is the aerial robotics. So most of the people do the quadrotor design, but what we have done here is to have a different design for the quadrotor to have increased endurance or to reduce the size of the robots with the same kind of capabilities as in other cases. So this one we called as vertically offset overlapping propulsion system, where the rotor wings are actually overlapping one over the other, so that we can have an increased diameter for the propeller and get more power for the travel. So that is how we actually designed this quadrotor and improve the endurance. So this is the prototype of the overlapped propulsion system. So there is an overlap, and therefore there is an offset also between the propellers. And so we try to understand what will be the effect of such overlap and offset. And we found that there is not much of power loss. And then we showed that this can actually increase the endurance of the quadrotors by having an overlap propulsion system. So we did the trials using, within the lab for testing the losses, and then finally did a test in the ground. I'm not sure the video is working. Yeah. So we did this test to show the capability of the quadrotor for, I think video is not working well. So, but we finally proved that this can actually have an increased endurance. Yeah, as you can see here, it's carrying a payload, and then showing that the payload can actually be increased by having this mechanism. Okay, so before concluding, let me present some other related work in the area of quadrotors. So in the guidance, navigation, and control, this is from the lab of Professor Satatal Ghosh in the aerospace department. So he's working on the planning and motion control of aerial robots. So this particular work shows the obstacle avoidance and dynamic collision avoidance of multiple quadrotors. When multiple quadrotors are deployed, how can they avoid the dynamic collision? So this particular work is related to offline motion planning and online reactive motion planning to avoid obstacles. And this is again additional work on path planning. So it's actually shows the target localization in 2D and 3D environments, as well as landing on a fixed or a mobile platform. So if a rotor aircraft has to land on a moving platform or a mobile platform, what kind of control strategies can be employed? What are the strategies need to be developed? So this is this work primarily looks at the landing issues. So these are the works from Professor Ayusawa. So I'll conclude with this presentation with this slide. So thank you very much for your time, and sorry for the difficulties encountered during the presentation. Thank you.
Thank you, Professor Asokan. So our next speaker is Professor Ekta Singla from IIT Ropar.
Yeah, thank you. Am I audible, please?
Yeah, you're audible, yes.
Okay. And the slides, I know.
Yes, they're okay.
It's in the presentation mode. Is it all right?
Yes.
Okay,
Yes.
thank you very much, Professor Ashish Dutta, and everybody. A very good morning to all the Indian participants, and a very good afternoon to all our Japanese friends. And it is certainly an opportunity, and I'm sure that it will be great to have this sharing with you, and the rest of the 3 days will be very effectively utilized. Okay, so IIT Ropar is relatively a new IIT in India, and as I say that it is around 13 years now. So we call it as the second generation IITs. So relatively, I mean related to the 3 other speakers which we have, like from Madras, Delhi, and Kanpur. So that is why I have just used 2 or 3 extra slides to advertise the institute, you know, because I would like that people should be here. In totality, I'll be speaking about the umbrella Punch Robotics. That is one of the, because it was a recently established institute. So when we were having only 7 to 8 faculty members in the Department of Mechanical Engineering, I never found anybody really that who would be working exactly in robotics. So in 2016, with the help of our RSI members themselves, we have established Punch Robotics here, which is a platform, and I'll be speaking about it, and in particularly the research areas related to the modular concepts, which we are focusing. Of course, there are many other directions in which students and the faculty members are working. I'll be just touching upon a few. And yes, as I just mentioned, we are at the northwestern part of India. And if I just would like to give a glimpse of our new campus, which we had shifted just 3 years back, because before that we were in a transition, in a transit campus. So although it was established in 2008, but 2010, it's like now only just 3 years back itself, we have shifted to this campus. And yes, I'm using a few more pictures because it will be nice that whenever next in person we'll have any conference, and then our participants, they must think about visiting the campus. And yeah, this is the Satish Dhawan block, the Department of Mechanical Engineering, where I belong to, and my lab. Just a glimpse, because of course every year people come and go, and in particularly I am working both in industrial robotics as well as touching upon many of the other areas in which we can, where modularity can be incorporated. But before that, yes, again, because about the location, as I said, I'll advertise a little more about the institute, because for our international participants, particularly the speakers, you know, another reason that why you must visit Ropar, which is less likely to be popular, is actually because this is one of the biggest sites belonging to the Indus Valley civilization, and we have a museum here. I'm sure you would like to just add in your next visit plans. And yes, there are many of the tourism locations around, and including the Golden Temple at Amritsar. And more than that, we were very fortunate enough that we have 10 in a very nearby, like around in the area of 30 to 40 kilometers itself. We have 10 more national labs and institutes, and which is helping us to develop the collaborations and interdisciplinary working both in medical as well as in materials, etc., in a very good pace. That is why we have got very good rankings also both nationally and internationally. Now about Punch Robotics, because as I said that in 2016 when we found that people are working in distinct areas, it was important to club them, that they had some idea about robotics but they didn't know exactly where to start with. That was the time when we actually started with the PR community, which is now increasing, in which we do have all industry faculty members and the students from different programs, and it is helping to uplift the sector of robotics, as well as because mainly people are working, all the faculty members may be into additive manufacturing, they were also into materials, the experts from different directions, they are now contributing under this umbrella of Punch Robotics, right? So what I'll be doing is, like, of course we had access of this PR studios not only to the IIT Roper students but to also around. There are so many institutes and colleges where maybe sometimes very few people are working in robotics, but now we are trying to club them. So this is one platform which is helping. And just to give a glimpse of some of the directions in which some small and big projects are working before moving to the modular concept. And this is actually like, okay, students have also utilized the facilities to work with the this humanoid, may it be into the speech gesture mapping, as it is just mentioned, because I'm just giving the limbs, and also for its movements, its arm movements, manipulation, etc. So there are 3 or 4 projects which are related to the humanoid. And similarly, in the vision sector, camera pose estimation, this is just the recent. I'm just showing the ones which are published and not just taken up by students, so that because it is still just 3 to 4 years old. But yes, I just picked up some. For example, this is the second one. This is in which we had seen that in many of our works we needed the entire the simulation or some collision avoidance, etc. in the environment. Many of my own works were related to the realistic environments. So how to get the environment built, like at least the STL files quickly using the scanner itself, without using the professional scanners. Now we have used the cameras itself, so that by taking some of the pictures, how we can construct the 3D scenes directly and use them in our other projects. And majorly we are working in the design analysis part, mainly may it be using the serial or parallel linkages. And modularity and reconfigurability manipulators, I'll be speaking more about it, how we have utilized it in 1 or 2 versions of modular libraries I'll be showing. And yeah, recently, because in the area we have got 1 or 2 like international as well as some projects from defense and the rehabilitation center from Delhi, where we are working towards towards how to just use the task base, because mainly you'll find that our work is related to the customized robotics, in which how to for any type of mechanisms can we actually incorporate that, how we can have more mimic, just following the actual human motion. And this is just, again, I would say some of the projects which are recently taken up in 1 or 2 years. And mainly I would like to just go further. Yeah, as I mentioned, in the right side, you will find that in the other works which are taken up mainly at the research directions, there we normally take up to cater the customization. And for customization, the majorly we take the task-oriented planning, the task planning, optimal synthesis, and also collision avoidance, minimum interference, unconventional parameters. We are also taking care of the parameters which are unconventional in nature. I'll be just showing about how we have used not just 0 and 90 of alpha of BH parameters, but we are trying to give unconventional architectures for some of the intricate this environment. And reconfigurability is what we have, what in my group we have actually utilized, or you can say explored in the last 3 to 4 years. And first, Moir is my own library, because I just mentioned modular and intelligent robotics. Mark 1 is actually the modular library which I would like to propose. This is how I started in 2010 in this institute, where in the first 3 to 4 years we were more into task-based planning, because we had looked for all the cluttered environments and how we can actually go for redundant and modular robots. Mainly we started with the redundant arms. You will see that how we have, for a cluttered environment, of some of the realistic examples we have taken from, say, from some power sector, power plants, or some of the our own labs. We were taking some of the cluttered environments and trying to see if we can actually develop a basic synthesizer robotic system which is redundant in nature. But it was all getting that only into the design side. We have seen that the unconventional designs, it was easy to just show in the simulation, but not really applicable when we actually see that we need to develop a robot, because the parameters were not exactly 0 and 90 or perpendicular to each other. So there we started with our work in around 2013 for modular library, and this was the first, I would say, set in which we had seen that all the systems, that how exactly it will, that given a particular task, how exactly we will be utilizing. First, we should know that, for example, here, if at the right side, rather I'll use this case study because it's from that first student of mine, 2013 to 15, 16. So basically there we had seen that if there will be a cluttered environment and we look for some robotic assistance for that and develop a system, of course not, of course using the modular robots, then what we do is that we first take the as an assumed model of that, for example, left side. Now for that only I mentioned that rather than now making a solid model separately, we were working on how to scan and directly using the pictures and how to construct the 3D construction. What work I showed earlier will be utilized here in this course also. And we have given that how we will be choosing, because using the modules which we had developed, these modules have been developed, which I showed in the previous slides, the first set of modules. They were, in 3 sets, like the 3 types of motors, accordingly the 3 lengths, and Y3 that everything was published related to that. What are the extent of robotic arms which we would like to develop? For example, till 7 to 8 degrees of freedom. Then what is the extent of payload, and can they carry each other? Why we cannot have same type of modules, and why do we have distinct, and how many, and for each module we also compute that how many more number of such modules optimally it can actually check. So everything was used, so enough of optimization techniques, different both classical and evolutionary for such methods. And by normalizing minimizing the talks, we had seen that how exactly for given task, if we just use the modules, then what will be the right modular manipulator which will be helpful to use in that particular cluttered environment. So this framework was ready, and recently in the same direction, we had actually developed the Mark II, we will say that improved library, because the first version was certainly heavier, and we had of course noticed many of the issues related, particularly it was not minimized, we had not checked the dynamics of it. So recently now we had worked for, analyzed, I'm not showing the details here, but yes, we that how the next, we have seen how the architecture of the entire each module needs to be optimized, and we have seen from the dynamics perspective also, because earlier we were looking at mainly only the static or the kinematics. So here it has to be seen that again the entire strategy. I'm just skipping this, but showing you this particular library, because now the set is ready. We have tried to make it of course lighter, and the actuators are changed. Earlier we were using the heavier version which were not required, and now, because in modular library it is very important to select the actuators first, and because they need to be appropriate, or you can say optimal enough to do the job as well as to carry each other, because the weight of the actuators or the gear system, etc., is also playing a role. So Anubhav here is my recent student who has actually developed this unconventional list. And here I would like to mention that we are not developing the robotic systems like how they are unconventional, because as you just see here, when they are connected, we can actually change the alpha to some different values rather than 0 and 90. So of course we can actually develop, we need to just compromise something like the rigidity, but basically to work in the cluttered environments and to help in the service robotics and for maintenance, where we are trying to take 1 or 2 case studies also recently. There we are showing that how the same modules can actually be able to, they can be assembled and reassembled or reconfigured to get different types of configurations which are required. So we have actually tested for many of these standard configurations which are required, and also we have incorporated particularly for unified modeling, because at present we have made it a point that earlier it was not so that we were not using the similar robot operating system like ROS, but now from the last 2 years we've also made it a point that why not to make it more standard. And what is happening is that using the URDF files and the standard, these platforms, we have now developed these arms, modular system, where anybody can actually utilize it for say given DH parameters and modular systems. If we know that what exactly is to be required to be assembled, then which modules will be able to, so all that, like there are limits which are already planned, so everything is done, and after that for a particular task which could be complicated and for a particular for an environment, it actually develops one system. And in fact, not only this develop, if you want to assemble on your own and then get your modeling, both kinematics and dynamic modeling, which for the system you have developed, that that unified modeling is also done through this standard, in this standard operating system, that is ROS, so that it can be now utilized by as open sources or by other people who are working in the same area. So just to show you this glimpse, because in one of the case studies, we have tested for a few case studies where we see that how the same modular system can be utilized. And here you will see that given any particular say the right side, any particular cluttered environment, if we use our earlier design systems, because I have been working, which I have not shown here, for the synthesis, for the optimal synthesis. So we, for a particular cluttered system, which optimal DH parameters or which optimal robotic arm will be useful for the given number of tasks. So tasks we always give as some standard points, as I have shown in the very beginning. And for those, if we just see that, okay, this is the system which may have 5 degrees of freedom or 6, and which modules is also being computed, because that also take care of the optimal, all the optimality in talks, right? So then we can actually develop, and first we can simulate both in the simulators which we have prepared, and also using the actual robotic, because this modular modules which we have developed in our lab, that we can actually demonstrate. So one of the demonstrations, for example, here, this was a cluttered environment, and how it will be the path planning, etc. Also we show through the ROS and the peripheral other platforms. So here, if my video is okay, 1 second, it will take a minute, like how exactly the modules work. Is the video working, please?
Yeah, the video is okay.
Because the entire idea is that using the other work, that if we get any realistic problem, environment in which, so we can actually scan it, get the environment, get the robot design ready through our design algorithms. And then once it is, we know that what is which TH parameters or which modules are to be used or assembled, then how straightforward at least to do the demonstration in our present version. So this is our second version, which we are trying to show that at different configurations. So I'm just fast forward. Okay, it is anyway going. These are all 3D printed in the institute itself. So certainly now we are collaborating with 1 or 2 industries to look after what are the shortcomings and what next we would like to work with our Mark III. And 1 or 2 industries have shown their good interest, and now it will be good for us to move further. And after some of the many of the feedbacks which we have collected on it, because we would like to increase on its strength also for the payload capacity, etc. And you'll see that similarly, the person actually showed this is one configuration, and now the configuration will be changed. So here the alpha is now neither 0 or 90. Now the alphas are working at different values, so that we can actually work in as required for the unconventional systems for the cluttered environments. So from here, I would like to also mention that the same concepts of, because in totality our groups are working in modular synthesis itself, not only because earlier the works which I have shown was mainly in the area of procedural arms, which we are also connecting to the industry for, where we know that because of the change in environment or any new system, suddenly you would like to change in the robotic configuration. So there we have connected. Similarly, now not only the serial, another student of mine, she's a part of Punch Robotics. So Sakshi, we are working with the modular synthesis with not only serial, but we have the loops also. We also see that how we can use the modular primitives having 4-bar loop or 5-bar loop, and then connect it together with serial. So we have actually developed a system, a modular system, in which we can see that serial and the parallel loops, they can be connected together. We are still at the planar robotic system, planar mechanisms only, but yes, particularly we are working for, because I got 2 projects but in the rehabilitation devices. There we see that how for a given exercise base, because as I said that we are working on the rehabilitation exercises, already 1 or 2 speakers have already spoken about it, which were very interesting, because we are in association with the rehabilitation center at Delhi, and there we have seen that how manually people are helping for the rehabilitation exercises, which is quite cumbersome. So through this slide itself, I'm just showing the entire process which we are working upon, because taking the trajectory of the 2 or 3 exercises one at a time, presently at the sagittal plane only at present, what we are doing is that can we develop such a system which is again customized for doing an exercise or for helping in an exercise for a particular person. Will be just planning doing the synthesis, which is the first step, which is and then for given primitives, and then this particular robotic arm is developed, for example, only in the sagittal plane. At the back, we are also working on the coupled that how to improve on the misalignment. So I'm just mentioning some of the recent works which we are trying to do, that how we are improving on the architecture and particularly the motion, using some passive joints also at the back. And yeah, when we are using all these hybrid systems, there we also see that we explore with many of the systems which sometimes we don't come into our mind. So what we do is we also have another work where you starting from the just generating the different architectures using the primitives, and then we see that how the same automatically in using our algorithms, we will see that okay, which are the active and which are the passive joints, and from there the automation in kinematics and dynamic in this we have just developed for the kinematic model, and that too using the performance criteria will be computed automatically, so that we can actually compare among the different generated generated configurations, and that is also helping us now, because in this rehabilitation work we have used 3 or 4 configurations where we need not to like any designer need not to start from the scratch of the models, and these unified modeling techniques using the modular primitives, we are using it, that how quickly we can actually analyze the different mechanisms which are developed using the modules, and then we can actually see if they can reach the task plan, because these are the points. For example, just symbolically I have shown here that how that if it has to go on these points which we have gathered for the task planning for the human motion which has been taken. So how good or which particular configuration is working better, right? Of course, at present we are working only for the kinematic analysis or kinematic performance, and even in that it is helping. And coupled, we also look for the coupled mechanism, because majorly in one of the projects we are working with the defense also for the leg exoskeleton, which are not used here. But there it is important, because we all know the problem of misalignment, because whenever we are using any particular robotic system, and we are also trying to do with less number of degrees of freedom, but if we'll go with it, certainly it will have the problem of compatibility with the human arm, and we are just trying to show it through simulation that how exactly the coupled system can be analyzed. So we have used here the screen theories and try to give the entire, the mechanisms which are unified models for the coupled analysis. So here I'm just clubbing that what is the entire process which this recent work from the last 2-3 years only, we have tried to give only the model and the simulation, where we take the data for a particular person, and then using that we just estimate the strengths, and accordingly, and also which exercise. Also quantitative model is given by the student, that this model will help us to quantify how much is the torque required, because given a particular strength, because so that which exercise and for how long it is required can also be given a priori without the help of any expert. And this is also to assist the experts, because we are working, as I said already, with some experts in Delhi. So they say that it will be helpful, particularly for the training of the next experts. So given a particular trajectory of a human arm, then how exactly we can work on the different primitives can be used to actually develop a particular system which will be suitable for that human person. And we also do some workspace analysis, because it is not that only for that particular trajectory it will be helpful. We have to check the performance around in the entire workspace, and then develop the particular system. And so here also I would say that it is almost towards the customized robotics, so that can we club it. Next one or two, some of the works which I have not shown here are actually to make the prototyping, directly from the primitives, so that if we know which is what system is suitable for a particular person, then can we customize it quickly or develop it quickly using the modules. So that is still in process. And similarly, we are working for the vertical farm setups, because we had seen that, because the library which I have shown, actually this is just a recent work which we are trying with the Innova cobot, but we would like to develop a library which I have already shown for taking care of the different agriculture processes which are required only for the vertical farms. The idea is that in the vertical farms, it's all actually, I'll better take it here. The farms are at present they are used only for 10 to 15 or 10 to 12 of height, and the robots which are in use are only which are working on the ground. So it is important, and also they are normally not the customized robots, but they are mainly the available arms which are utilized for this purpose, which is expensive if we would like to use everywhere. And looking at the Indian agriculture, where we are also we need to be having economical systems, there what we are showing is this is just the concept, the modular concept, where we see that not only in the layout, but height also we would like to at least make double or triple, so that even in the less space we can actually use the robotic system which can work on the rails. And there for each module, what I have shown here is one module, the concept, and for each module or modular the library will be able to work, and then of course it will shift its base and actually work for the next. So all the processes which are required may be related to seeding or transportation, or we are working on what are the different grippers required. We are also working on different end effectors which are required for the purpose. For example, just one which is shown in the right side here. But yes, this is again in the initial stage, and just recently, a few months back only, we have made an experimental setup. So I've not included it here, but I'm just showing that how what we are trying to give customization or modularity even in this, because these all here we are testing to begin with only with the Kinova robot which we have. But as I said, our vision is to look at the modular library which can take care of many agriculture processes, but only for the vertical farms, because the choice of the plants will be very specific, right? So it's not the field robotics, like not really the heavy duty. And here, finally, I'll also would like to mention here the modular concept, which, because as I said, different people also were working in different directions. So we were clubbing together that how exactly their expertise can be useful. And here I've mentioned is the agriculture at the top, but actually it is actually into the surveillance, because we would like to give some robotic skin for establishing some camouflaging devices, and there just to follow how natural camouflage work, we are using the electrochromic devices at present. Some of the research related in here, professor who is into materials, Dr. Prabhat, he is actually working with me, and in the other works like Dr. Anupam Agrawal from who is helping, who is actually using his additive manufacturing skills, particularly what I work in earlier for the agriculture and for the modular robots. And we have Dr. Shrikant from aerodynamics. So different people who are working. I've not just included their pick here, but yes, this is all that how their expertise in materials we are trying to put up for the surveillance sector. And here you will see that the polymers, we are just testing them, and the entire process is that how we can utilize, we can actually work on the different properties of those polymers, so that we can actually give. This is very recent, like kind of a few weeks back, we have shown that how we can develop or get the specific colors which are required, and how much time the color will stay, and if we want to change the color, how much time it will take. So all these testings are still in process, and what is the entire ways that can we actually develop skin which is modular, so that we can have this camouflaging skin which is made up of different ECD and just a 4x4 or a 5x5. We have at present seen that for these, the size of the minimum is 2.5 inch. So can we actually develop? We are working towards such kind of platform, but yeah, I've not given because they wanted to patent it, so we tried not to put up the actual conceptual pictures. And so this is all from my side. Yes, it was probably shorter, maybe enough to present the IIT Roper upcoming things. And as I said, this is I wanted to particularly emphasize on the very active environment here under Punch Robotics. And thank you very much.
Thank you, Ekta, for your nice talk. I think there's a question for you also, so please answer the question in the Q&A part. Okay. Yeah, so thank you for your talk.
Yes, thank you very much.
So now we have the last talk, that is myself. Okay, so 12:15, we are running late by 15 minutes.
Okay. How to, we need to respond now, or I'll be answering later?
You can answer later, it's up to you. Is my screen visible?
Yes.
Yes.
Okay. So good afternoon to everybody, and I'm the last speaker. So I'm Ashish Dutta, and I'm a professor in the Department of Mechanical Engineering, and I'm also the Dean of Infrastructure at IIT Kanpur. So today morning we have all met at IIT Kanpur virtually. So this map shows Japan on the extreme right, and IIT Kanpur is somewhere near New Delhi, somewhere in the middle on top. Okay, and so we have met virtually. Hopefully next time we'll all meet in person. Now, the broad areas of robotics research in IIT Kanpur, the way it is divided is we have the Center for Mechatronics, which is an interdisciplinary center between mechanical engineering, aerospace engineering, computer science and engineering, and electrical department. And apart from the Center for Mechatronics, we have the Flight Mechanics and Helicopter Laboratories. We have Intelligent Systems Laboratory, where people look at things like AI and machine learning. Then we have Computer Vision-based laboratory in electrical engineering, and Motion Planning Laboratory. So we have about 12 faculty members in the area of robotics, and it is interdisciplinary. So there are people in mechanical engineering, electrical engineering who are working together. Okay, so what I'll be showing you is interdisciplinary work may not belong to one particular faculty only. So the first is right from the basic dynamics of compliance systems. So most of the humanoid robots that are made, they're made up of rigid links. And we know nowadays that if we use series elastic actuators or we use compliance in any of the links, then what will happen is that the dynamics changes. Now it has some advantages in terms of stability, in terms of impact. So here, basically what we are looking at is compliant designs of biped robots, humanoid robots for walking, jumping, what effect compliance has on the dynamics and things like that. Okay, so design, control, dynamics, simulation is all included. Now, in most of the research work, we also try and build systems so that at the end of it, we have experimental results, and then we can also try and entice the industry if they're interested. So this is an area of compliant dynamics of biped mechanisms. Now, most of the bipeds or humanoids that are there, they are very, very good as far as they work inside the labs. But the moment they come outside, then we have trouble. Okay. Now, so we're also looking at how to bring robots out into the environment, not only in structured environment, but also in unstructured environments. So, for example, in three-dimensional terrain, walking in places with ditches, crossing obstacles, etc. Okay, so this is extension of humanoid gait planning, motion planning in 3D. Now, we were also a part of the lunar rover mission. So ISRO is the Indian Space Research Organization. And in 2019, they had sent a rover to the moon. And we were involved in that in terms of the motion planning for the rover. So the rover is a basic rocker bogie type structured system, which has a manipulator on top. And our job was basically to do the motion planning algorithms for this rover. So we also built a rover, carried out various studies on dynamics, motion planning, control, and then some of these were actually tested on the actual rover. Now, so this is motion planning for the ISRO Chandrayaan-2 lunar rover. Now, there are some interesting problems here. The interesting problem is that the landing was expected to be on the dark side of the moon. Now, on the dark side of the moon, there is no light. Okay, so you need to see at night or when there is no light. So cameras won't do. So the other task that we were interested with is how can you make a map without using vision, computer vision. And what was done there is we tried to use structured light. So this is a lab model. This is not the rover that actually went, but this is a prototype. And what we basically tried to do is to use structured light, but you use a line laser. And then using a camera, can you scan the surface and then generate a map so that you can see in the dark. And once you can see in the dark, then can you do motion planning of this 14 degree of freedom system to go from one point to another point. Of course, you have to do dynamics, control, simulation. And so we use 3D structured light approach for this, and we were able to generate maps, which you could actually see at night or when there is no light. Now, unfortunately, while landing on the moon 2019, I think, or 2 years back, unfortunately it crashed. And so we couldn't test our motion planning algorithms and also the visual generation algorithms. And next year, I think there is a joint mission between Indian Space Research and Japan Space Agency to go to the moon, where the lander will come from India and the rover will come from Japan. I think that is planned for this year end or next year. So this is about our studies on lunar rovers for motion planning, dynamics, control, vision-based navigation. Now, we also do work in the area of for rehabilitation, mainly for stroke rehabilitation. That is, you look at various motions, like grasping, moving for the fingers, for the hands, for the legs, and then try and design mechanisms which can give you back that motion. Okay, so this is some research which we had done for design of hand exoskeletons. Professor Shibata was also included in this project. We started off many years ago, almost 10 years ago, I think. And then we have progressed quite a lot. Now, the objective is to study human motion and then build mechanisms which can give you back that kind of motion, essentially because we have a varying instantaneous center of rotation. And the objective of this study was that, or the hypothesis here, is that if you're doing passive physiotherapy, that means the person is doing exercise with a physiotherapist, but the person is not thinking, which means the brain is not engaged. So if you can force the person to think and bring it in sync with the physiotherapy or the physical practice, then our hypothesis says that the recovery is going to be much, much faster. Okay, and that is basically where we started off. So we have a hand exoskeleton and we have a BCI, a brain-computer interface, which basically checks whether the person is thinking correctly. And if the person is thinking correctly, then only it actuates this device. Okay, so this is a part of our India-UK project in which we designed various kinds of hand exoskeletons for rehabilitation of stroke patients. And we also carried out a large number of clinical trials. Now, this is basically what the paradigm looks like. Okay, so we have a BCI cap, and on the screen, you can see a closed hand or an open hand or do nothing. And if the person thinks correctly, then only the exoskeleton actuates. Now, the hypothesis being that if it is in closed loop control, closed loop in the sense the person is also seeing, so there is visual feedback, the person is also feeling, there is physical feedback. So if this loop is closed, you are going to get a faster recovery. And we carried out clinical trials. Now, this has mechanical design, control systems, assist as required controllers, because if it is passive, the person will simply relax. He won't do anything. Okay, so you have to allow the person to try, and only if the person is not able, only then you should be able to help the exoskeleton. Okay, so that is where we try to design assist as required controllers, which are also for robots for assisting with humans. Now, we carried out clinical trials in India and the UK, and the results were surprising. So we know that for stroke, basically after 6 months or 1 year, you are not going to recover anymore. You do physiotherapy for 6 months or 1 year, and then you're saturated. Beyond that, nothing happens. Okay, but we took patients who are actually saturated after a year. So more than 1 year, 2 years, and we carried out this exoskeleton-based rehabilitation, and we found that 100% of them recovered, which is not possible as per physical physiotherapy-based physiotherapy. Okay, so these are some results of the experiments in India and the UK. And we have finished clinical trials. We are going in for large-scale trials now, where we want to try out in different countries to see the effectivity on stroke population. Now, in terms of the cognitive science, these results show that there is recovery, okay, but why is the recovery happening? Is it that the neurons are regenerating, or there is something else happening? So we also looked at the MEG imaging of the brain using MEG. And what we did find is something interesting, that not only is the neurons reorganizing at that particular location at the motor cortex, so we know where the motor cortex is and which actuates the arms or the legs, but there were new pathways which are being generated. And this is what we found, that the recovery is happening not only because of neural reorganization, but it is also happening because of these new pathways which are being generated from other parts of the brain to actually help. So we are looking at the engineering side, design, recovery, physiotherapy, but we're also looking at the cognitive sciences and trying to study that why is the brain behaving this way, or what is really happening at the brain level. Now, we also have done this experiments for the leg exoskeletons, and further trying to look at MEG-based studies for the leg exoskeleton also. We have extended our work on BCI-based exoskeleton, where we mounted the exoskeleton on a wheelchair, and we also have an eye tracker. Okay, so we have an eye tracker, which you can see here. So depending on where the person is looking, the wheelchair can be actuated, and the exoskeleton can also be actuated simply by using an eye tracker. Okay, so we have gone one step further in trying to provide locomotion ability to stroke patients. Another extension of this is something interesting, multimodal interfaces for communication and rehabilitation. Now, if a person cannot speak, okay, but you can enable a person to communicate by using this eye tracker-based communication interfaces. So this is basically for in the Hindi language, that is Indian language. So simply by looking at the screen, the person can actually type sentences for a person who cannot actually speak or cannot use his or her hands. Okay, so this is something which we had done using eye tracker for Indian languages. Now, this is the other area where a lot of people are working is AI, machine learning. So there is Dr. Behera who works on machine learning applications to robotics. And they look at things like autonomous grasping, which is what was done for the Amazon picking challenge. Okay. So if there is a cluttered environment with a lot of objects, how do you learn grasping without getting into the mathematics of grasping, without finding form closure, force closure? How do you get into learning how to grasp an object? And these objects are of different types. For example, objects of daily living. And in the Amazon challenge, I think they won the 3rd prize that year. And every year there is some challenge or the other, and they're very active in that area, using machine learning and AI techniques for learning-based systems. We also look at industrial projects for using automation. Now, this is an application of engine inspection. So for engines, especially trucks, when the truck has gone for about 10,000 or 20,000 kilometers, they need to inspect the engine. And the only way you can inspect the engine is to open the engine and then to look inside the piston, the cylinder, right? And this takes time and it's expensive. So what was done here is they devised an automatic method in which you have a probe, which is something similar to the laparoscopic probe. So we have a very small probe, and this probe, which contains a camera, okay, and has LEDs to provide light. This camera-based probe is inserted into one of the holes. So on the left side, you can see the engine is not open, but you can access it, okay, from the spark plug. So they can insert it there, and this automatic system can rotate and get the image of the inside of the piston. Now, based on this image, can you tell what is the state of the cylinder of the engine? So this means without opening an engine, can you do it in 5 minutes and tell what is the state of the engine of the car? Okay, so this is some kind of AI-based or machine learning-based application using computer vision. This has been sold, I think, to Tata Motors, and they are trying to use it in their truck business. Now, moving on to aerial robotics. So Iit Kanpur is probably the only institute which has its own airstrip. So we have an airstrip of 100-meter runway, and there are aircrafts which come here routinely, and we have our own aircrafts, which have 6-seater aircrafts plus gliders. So the next time you come to Iit Kanpur, please do take a trip or visit our airstrip and take a joyride around Kanpur city. Okay. So in terms of aerial robotics, we have the aerial robotics, which is basically winged aircrafts. Then we have helicopters. Then there are a cross between helicopters and winged aircrafts. And the aerospace department, which is very big here, and they basically look at the complete range from design, simulation, modeling, then motion planning, vision-based control, okay, the full gamut of expertise in this area. And there is a very big lab for helicopters, especially because helicopter flight is supposed to be difficult to control compared to a winged aircraft. So these are some of the pictures. The left top is the airstrip, okay, and these are some of the robots which have been made at home, and some of them are for the defense forces, and others are for research in different areas of control, autopilot, motion planning. So these are some of the aircrafts which have been made, fixed wing UAVs. Then we have tilt quadrotors, quadrotor convertible planes, and then conventional quadrotors, IC engine helicopter, then variable pitch quadrotors. Now this IC engine helicopter is something interesting, that they are not using electrical motor, but they're using an IC engine, okay, which is a small IC engine, the one that is used in motorbikes, or much smaller version of that, to fly the helicopter. And in terms of design, they have looked at various types of designs. For example, the VTOL concept. So there is also a company which is there, which is trying to build an actual VTOL aircraft. So this is the top one on the center is a compound helicopter. So there is a quadrotor convertiplane. Okay, so this is, you can see it has a helicopter rotor on the top, and it has blades in the front. So it is a compound helicopter. On the right is a quadrotor tail sitter, and then we have a quadrotor convertible plane, which can convert to a fixed wing. It can fly like a fixed wing aircraft, or it can fly like a quadrotor itself. So these are some of the research areas they're working on. Swarm architectures for communication between different kinds of aerial vehicles, helicopters, fixed-winged aircrafts. Some homegrown new kind of quadrotors, so engine-based quadrotor, where There is no body here. It is fixed straight to the quadrotor, and then you have a quadrotor which is an engine-based quadrotor. Okay, these are prototypes which have been made and tested. Then novelly fully actuated tilt augmented quadrotor helicopter. I'm not in this area, so I'm not very familiar with what this is, but what I understand is you can tilt the quadrotor and then it can behave like a helicopter if required. The other area where we have been working on is micro robotics. So at the micro scale, you need to make devices. So there is a National Center for Flexible Electronics where they make micro devices, sensors, small robots at the micro scale using flexible electronics, printed electronics. And we are also working at the micro scale where we can make very small devices, very small linkages for robots and users. For example, making micro holes, making micro sensors, which are used in robotics applications. So I think my time is up, so I will stop here. So thank you for your attention. Yeah, so I was the last speaker, so I thank myself.
Yes, I did. Thank you.
Okay. So I will stop sharing. We can have a very short discussion. I think we had a long morning and a long afternoon. So we can have a very short discussion and then we can end the workshop session today. So at the very beginning, I'd like to echo what Yamazaki sensei said today morning, that he was not very sure of what is the objective of this workshop. Okay. So I will echo and say that I was also not very sure what is the objective of this workshop. I think none of us were sure. Okay, but as there is an old proverb that a long journey begins with a single step. So I think this is the first single step, that at least we know that you're there and we are there, and we can have some kind of a long journey onward, right? Shibata, what do you say? So,
So yeah, I totally agree with you. Thank you very much. So this is, I actually learned a lot from your presentations, even from Japanese presentations. So yeah, so we'll be able to develop. So yeah, from now on, yeah. So we'll have. I think we'll have this kind of workshops. You know, at least you know, once in a year, and maybe more, and always need to consider. So let's consider to develop actual collaboration. I mean, human resource exchange, or you know, start getting some grants together, or develop some grants together. For example, JST, DST grant, and also some yeah. So let's start personal contact also. Yeah, and thank you very much. I'm really happy to be here. Thank you very much.
Yeah. So if anybody would like to share their views as to the way forward. Yeah.
Yeah. Can I speak?
Yeah. Who is it?
Asokan.
Yeah.
Yeah. So thanks to all the speakers for all those presentations, and it was very interesting to know about the type of work going on different places. As Shibata mentioned, we may not be knowing what is the work going on in our own place or nearby places. So this kind of workshop helps us to understand the diversity of work, research work going on. So it was it was nice to attend and listen to all the speakers. So as you know, this the proposal for this workshop actually came during our GBM, the body meeting, and Professor Shibata agreed to coordinate from the Japan side to have a workshop, which will be the first step towards a better collaboration with Japanese researchers, maybe between TRS and RSJ in the beginning, and then we can actually expand it to other universities and other faculty also. So we can actually start discussing with individual faculty. So I found that there are many people who have common interests. So we can start individual discussions and then see how that can actually be taken up as either a big project or through some individual collaborations. But in any case, we need to keep the momentum on and then try to see how best we can utilize this to take it forward for better collaboration with India and Japan. Once again, I thank all the speakers and all the participants for attending this. Thank you.
So, thank you. So, Professor Joante Venture, Professor Joante
Yes, I really wanted. Can you hear me?
Yes.
Yes.
Okay, good. Okay. So I really wanted to thank you for the opportunity. I was a little bit like Kimitoshi at the beginning. I wasn't sure about what would be like what we'll be discussing and how things will turn out for the workshop. I am super happy we had this workshop covering all the activities that you have. And to follow up on what Tom was saying, so there is this like GST, DST program, but there is also a GSPS, DST program that I was very lucky to have, and I did some collaboration with some Indian colleagues at NIT Rourkela, and there are multiple opportunities, but these are like opportunities between two researchers, one in Japan, one in India. But I think it would be really amazing, as also Tom said, if we could follow up with a yearly workshop, either in coordination with an international conference or outside an international conference, just to continue the discussion, because so many of the presentations today were amazing, and there's so many things to discuss and to and so yeah, I'm super excited actually.
Thank you.
So thank you
Ashish.
actually, Venture Sensei, Professor Venture, so for organizing
Yeah,
the
we should
Japanese
thank
side
Professor
speakers. Thank you very much.
Gentiane Venture for the Japan side. I think we should thank her. I was waiting for the end to thank her, but I'm thanking her. I'll thank her again.
Yeah, Ashish.
Yeah,
Saha is, yeah.
Yeah. Well, thank you for this nice opportunity. And what I wanted to propose to the RSJ now to consider being a co-sponsor of this AIR series. So far, I think they are not supporting this thing officially. That is one thing I request RSJ to consider, number one. Number two, in the list of their supported conference, then automatically, AIR will be visible. That is one from the RSJ side. The second is the collaboration. Of course, certainly, GSPS, DST. In fact, there was an attempt a few years ago, DST, GST, in the area of robotics, but actually it was a cyber security which has won the big grant from DST, JST. But certainly GSPS is another one, but those are mostly from the research. We may facilitate those activities, but I think co-sponsorship of this RSJ to AIR, that's number one. And number two, this annual workshop should continue. We have 1 year AIR and another year is a workshop. This workshop should continue as we have done it today. Thank you.
Thank you, Professor Saha. Yes, I think technical sponsorship from RSJ, yes, I think that is something that we can work towards. Yeah, anybody else? Professor Yamazaki Sensei, would you like to say something?
Thank you very much. I'm happy if we have some collaboration. Yeah, thank you today. That's all.
Okay, thank you. Anybody else? Ekta and,
yeah, actually, this is all about first thank only for the entire all these speakers. And in fact, as I have already mentioned about our local ground here, the platform about robotics, the way our national society, that is Robotics Society of India, is helping us to uplift, because the way we'll be connected together at the national level. Now I'm sure that RSJ will be taking their help to uplift, because otherwise without these workshops we'll always keep thinking, oh, maybe we don't know when we go to Japan and what is our targets to really incorporate. So I would say, like, why only after an annual, because annual events are too far these days. Annual is like workshop or a conference anyway we are doing. So these online thinking, of course, we could not enjoy the coffee from Kanako today, but this online sessions have helped us that how by giving only half a day we can actually conduct more. So maybe if you can consider about little more such workshops, maybe at least in 6 months next, rather than waiting for 1 year.
Yeah. Okay. Thank you.
Thank you.
So anybody else?
From the participant side, you may give an opportunity, other participants.
We have Q&A actually, basically.
Achha.
So I think, no, there are no more questions.
Actually,
Okay, so I think we can end today then. So at the end, I would like to thank from the Japan side, Professor Yuante Venture, who has collaborated from RSJ side, Professor Tomohiro Shibata for the great idea of getting it started, and everybody else. So we are collaborating. RSJ does help. Professor Shibata manages to get us reviewers for our papers. So that is collaboration. Okay. And I also help him by reviewing some of his papers. So that is also collaboration. And yes, we should move towards having technical collaboration from RSJ and also having this workshop yearly, 6 monthly. Okay. One issue is that people wanted a conference. We also have something called the Asian Robotics Society. You might be aware of that. Okay. And there was a proposal to have an Asian robotics conference. Okay, through the Asian Robotics Society. But however, it was felt that there are too many conferences. Okay, people are running from here to there. There is conference every day. Okay, so maybe having another conference is not a good idea. So we should collaborate more. Okay, and look for this DST, JST kind of funding opportunities in the area of robotics, and also through informal meetings and collaborations. So thank you all very much today. So let us please do attend AIR. It's open to you all. The link is the same. So whenever you have time, please drop in. Okay, the AIR conference
Dutta,
is...
1 second. When to answer this? Because many people have not written. It was mentioned that we'll answer during the session. Or is should I write here?
You can, yeah, you can write.
There's 1 or 2 questions.
Yeah, there is one for you. So you can answer it now.
Yeah, so it was, I was about to write, then I thought probably we'll discuss. Anyway, the question is regarding the number of modules, how it will be decided for a particular task. And actually we work in 2 or 3 phases. In the first phase, we decide on the number of degrees of freedom, that is the optimal synthesis phase, in which based upon the task, which is actually the number of points and their orientation, so what position and orientation, you actually decide the optimal number of degrees of freedom along with the optimal values of pH parameters. So whatever is the number of degrees of freedom, that gives us the idea of the modules to begin with, and then at the later stage we just do some kind of validation also. So at the first stage we decide on kinematic, based upon kinematics only.
Okay, thank you.
There is one from our Asokan.
Yeah, there is a question for me. So can the underwater robot which was presented initially be used for dragging a survivor to the shore? So this robot is not exactly for that purpose, because that is only a surface vehicle can do this kind of dragging a survivor to the shore. But salvaging an object from underwater, yes, we may be able to do it by properly attaching a manipulator arm to the vehicle. But otherwise, an underwater robot is not exactly for getting people out of water. That maybe we may have to have a surface vehicle and attach with its own arm or other attachments, and then can be used for dragging a survivor. That's my answer.
Okay, thank you. Then let's end the session today. So thank you, everybody. So I would say arigato gozaimashita until the next time.
Thank you very much.
Thank you, Ashish. Thank you all.
Thank
Hi
you.
all. Yeah.
Okay, bye.
See you in the.
Bye. Yeah.
You want to make that announcement?
There are participants are there, right? Yeah.
Yeah.
Okay, so the next announcement for the participants is